What would happen if we were alone in a universe so vast it exceeds our understanding of existence? The Fermi paradox challenges this idea by questioning why, despite billions of stars and potentially habitable planets, we have not yet found signs of extraterrestrial life. This exploration delves into the cosmic phenomena that awaken even more curiosity: the mysterious fast radio bursts that resonate in space, the wandering planets without stars, and the disturbing emptiness of cosmic voids. Each one of these elements serves as a clue in an intricate puzzle about the nature of our universe. As we travel through anomalies and inexplicable observations, we face the accelerated expansion of the cosmos and the galactic mysteries that remain tantalizingly out of our reach. The questions that we ask today shape our search for knowledge tomorrow. Join this expedition not only to see and seek answers, but to embrace the wonder of the cosmos itself, expanding the limits of what we believe we know. The Fermi paradox is a fascinating enigma in astrobiology and cosmology that poses a simple but profound question. If the universe is so vast and potentially teeming with life, where is everyone? Named in honor of the physicist Enrico Fermi. The paradox highlights the contrast between the high probability that extraterrestrial civilizations exist in other parts of the universe and the lack of evidence or contact with such civilizations. Scientists have calculated that, given the large number of stars in our galaxy and the probability that planets orbit them, many could harbor life forms. However, despite decades of searching through various methods, such as radio signals and space missions, we have not yet found any definitive sign of life beyond Earth. This total absence of evidence, despite the immense odds favoring the existence of life elsewhere, is what sparks curiosity and bewilderment around the Fermi paradox. Many theories have emerged to explain this paradox. Some suggest that intelligent life is extremely rare, a possibility that leads us to think we could be unique in our capabilities. Others propose that advanced civilizations tend to self-destruct before they can communicate or travel great distances through the cosmos. Furthermore, it is conceivable that highly developed societies avoid making their presence known, either out of caution or because they deliberately choose not to interfere with less evolved civilizations. The paradox invites us to reflect on profound questions about our place in the universe, challenges our assumptions about life beyond Earth, and provokes debates about the nature of intelligence, technology, and existence itself as we continue to seek answers. Among the stars, the paradox continues to fuel our imagination and scientific investigations, reminding us of the mysteries that still lie beyond our understanding. The Drake equation is a fascinating formula that attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. Developed by astronomer Frank Drake in the early 1960s, it incorporates several factors such as the rate of star formation, the fraction of stars that harbor planets, and the number of planets that could potentially harbor life. This equation serves as a framework for scientists to consider the possibilities of life beyond Earth, inviting stimulating questions. Are we alone? With how many civilizations could we be sharing the cosmos? On the other hand, the Fermi paradox presents a compelling contradiction to the optimistic projections of the Drake equation, named after physicist Enrico Fermi. The paradox highlights the apparent silence of the universe despite the large number of stars and planets that could harbor intelligent life. Given the high probability that numerous civilizations exist, one would expect to detect signals, technology, or even the civilizations themselves. However, we still find ourselves searching the vastness of space without receiving any clear evidence of extraterrestrial life. The interaction between these two concepts raises profound questions about the nature of life in the universe. If we assume that the calculations of the Drake equation suggest that intelligent life should be abundant, the Fermi paradox challenges us to explore why we have not yet found any. Are advanced civilizations choosing not to communicate? Could they be using technology or methods of existence that we cannot even conceive, or could they be ephemeral due to self-destruction or other cosmic events, which would mean that civilizations rarely coincide in time? As we delve into our understanding of the universe, both the Drake equation and the Fermi paradox remind us of the vast unknown that lies beyond our planet. They challenge us to think critically about life, intelligence, and the countless factors that could influence the development and longevity of civilizations in the cosmos. In this search for knowledge, we continue to look to the stars, imagining what could be out there, wondering if we will ever come into contact with our distant cosmic neighbors. The Fermi paradox captures the intriguing enigma of our universe. It raises the question of if the universe is vast and teeming with billions of stars and potentially habitable planets. Why have we not found aliens? This paradox leads us to several fascinating solutions that researchers and scientists have proposed over the years. A popular solution is the concept of the Great Filter. This idea suggests that there is a stage in the evolution of life that is extremely unlikely that most civilizations can pass. This filter could be behind us, such as the emergence of simple life from non-life, or it could be ahead, indicating that advanced civilizations inevitably self-destruct before they can colonize the galaxy. If that is the case, the absence of signals from extraterrestrial life does not indicate our failure to find these beings, but rather the difficulty of achieving a lasting civilization. Another intriguing possibility is that intelligent life is extremely rare, with many planets potentially developing life, but very few nurturing it to the intelligent stage. The requirements of the right conditions, the right time frame, and a multitude of cosmic events make the emergence of intelligent life extremely rare. This has led some to consider that we could be one of the few, if not the only, intelligent civilization in our galaxy or even the universe. The idea of a cosmic quarantine also adds another layer to this mystery. Imagine that advanced civilizations are intentionally avoiding contact with us, either to allow us to develop without interference or because they have decided that we are not yet ready for contact. This non-interference policy could reflect a universal principle about the development of intelligent societies. The idea that they're simply watching us from afar adds an element of drama to our loneliness in the cosmos. Finally, we can contemplate the immensity of space and time. The universe is more than 13 billion years old, and civilizations can arise and disappear throughout its life. Given that we are only a fraction of the way on the cosmic timeline, many civilizations may have existed before us and become extinct, possibly before they could reach us or even be detectable. Each of these solutions opens an exciting door to understanding our place in the universe, leaving us to reflect on what awaits us in our search for answers in the midst of the stars. The Great Filter is a thought-provoking idea that seeks to address the enigma presented by the Fermi paradox. In essence, the Fermi paradox poses a simple but profound question. If the universe is so vast and old, full of countless stars and potentially habitable planets, why have we not found signs of extraterrestrial life? The Great Filter proposes a possible explanation for this silent cosmic landscape. This concept suggests that at some point in the evolutionary line, there may be a significant barrier or filter that prevents life from advancing to a stage where it is technologically capable of communication or interstellar travel. This filter could occur at various stages of development, such as the emergence of life itself, the evolution of intelligent beings, or the development of advanced civilizations. If the Great Filter is behind us, it means that intelligent life is extremely rare or that life is rarely able to reach an advanced technological stage. Alternatively, the filter may be ahead of us, suggesting that humanity has future challenges ahead that could hinder our evolution or lead to extinction. This perspective raises existential questions about the sustainability of our civilization, our capacity to face challenges like climate change, nuclear conflict, or other existential threats. If we want to survive and prosper, we must face these obstacles head-on. Embracing the idea of the Great Filter invites us to reflect on our place in the cosmos, encourages us to consider the unique conditions that led to our existence and appreciate the fragile nature of our civilization. While contemplating the infinite extension of the universe, and grappling with questions of life beyond our own. The Great Filter remains a compelling concept to understand our cosmic journey. The vast scale of the universe plays a crucial role in the formation of the Fermi paradox, a concept that questions why, given the immense number of stars and planets, we have not yet found evidence of extraterrestrial life. This paradox has its roots in the sheer size of the universe itself, with billions of galaxies, each with billions of stars and countless planets orbiting those stars. One might expect that alien civilizations are common and that we had already found them. However, the vast distances between these stars pose a significant barrier. Even with advanced technology, reaching other star systems would take an immeasurable amount of time. For example, our closest star, Proxima Centauri, is more than 4 light-years away. At the speed of our fastest spacecraft, it would take thousands of years to reach it. This reality means that, even if intelligent life exists elsewhere, the chances of us coming into contact or even being aware of its existence are slim due to the tremendous distances involved. Another aspect to take into account is the universe's age. The universe is approximately 138 billion years old, which allows plenty of time for life to arise and evolve. However, this time span also means that many civilizations may have arisen and disappeared long before we arrived on the scene. If intelligent life evolves, it could persist only for the blink of an eye in cosmic terms, disappearing due to self-destruction, planetary catastrophes, or other unknown factors, while the universe continues without them. Finally, the immensity of the universe can also influence the types of civilizations that arise. Many planets may be found in inhospitable environments that severely limit the development of advanced life. Furthermore, with so many worlds to explore, the probability that an advanced civilization directs its attention towards the stars could be low. All these factors intertwine to amplify the enigma of the Fermi paradox, leaving us with profound questions about our place in the cosmos and the nature of life itself. The Fermi paradox raises a puzzling question. If the universe is vastly large and potentially teeming with life, why haven't we found any sign of extraterrestrial civilizations yet? The different models of planetary habitability offer ideas that can reshape our understanding of this intriguing dilemma. These models help us assess the likelihood of life on other planets by examining various environmental and astronomical factors that contribute to a planet's ability to sustain life. A significant factor in these models is the concept of the habitable zone. This is the region around a star where conditions may be suitable for liquid water to exist on the surface of a planet. The Earth is perfectly situated in the habitable zone of the Sun, often called the Goldilocks zone, where it is neither too hot nor too cold for liquid water to exist. By applying this concept to other star systems, researchers can identify potentially habitable exoplanets. However, the simple fact that a planet is in this zone does not guarantee that it has developed life. Factors such as the planet's atmosphere, geological activity, and magnetic field also play a crucial role in fostering a stable environment. Furthermore, recent advances in planetary habitability models highlight the variations in conditions that can sustain life. For example, some models suggest that life could thrive in extreme environments, such as those found on icy moons like Europa or Enceladus, which could harbor underground oceans. These insights indicate that the diversity of planetary environments in the universe could be much greater than previously thought. Therefore, our search for extraterrestrial life may have to expand beyond traditional habitable zones to include these less likely but fascinating possibilities. The implications of these varied models can lead us to reevaluate the assumptions linked to the Fermi paradox. If life requires a wider range of conditions than is usually considered, then the absence of detectable extraterrestrial signals may not reflect a lack of intelligent life, but may suggest that we are looking in the wrong place or simply that civilizations may be rare, ephemeral, or exist in forms or technologies that we do not yet understand. Ultimately, as we continue to explore planetary habitability, We may discover new paths that bring us closer to understanding our cosmic neighbors and perhaps even finding traces of their existence among the stars. The zoo hypothesis offers an intriguing perspective on the Fermi paradox, which asks why we have not yet found any indication of extraterrestrial civilizations despite the immensity of the universe. The essence of the hypothesis suggests that advanced alien civilizations are deliberately avoiding contact with humanity, just as zookeepers try to minimize interference with animals in a zoo. This idea proposes that we are being observed from a distance, similarly to how we might observe animals without disturbing their natural behavior. One of the key reasons why advanced civilizations might choose to remain hidden is the notion of a cosmic ethical guideline that prioritizes the development of less advanced species. Such a stance could stem from the desire not to interfere in our natural evolution or cultural progression, refraining from direct participation. These civilizations allow us to grow and mature on our own, fostering our potential without imposing their own technological advancement, which could alter our social fabric. Furthermore, the zoo hypothesis implies that there are likely many other forms of intelligent life throughout the cosmos that are equally under observation. If this were the case, the universe could be teeming with life, although most of it remains invisible, as it is governed by this code of non-interference. This adds a layer of complexity to our understanding of life beyond Earth, suggesting that contact may not be an absolute certainty, even if civilizations are aware of our existence. This approach to the Fermi paradox challenges conventional notions of what it means to communicate and interact as intelligent beings. It invites us to consider the possibility that the universe is not just an empty extension, but a dynamic network of civilizations united by their own rules of engagement. From this point of view, the stars could shine not as distant and unattainable entities, but as beacons of life watching over us, with their gaze ever present, though invisible. The Fermi paradox raises a fascinating question. If the universe is so vast and potentially teeming with life, where is everyone? An intriguing perspective on this mystery involves the concept of self-destructive civilizations. This theory posits that advanced intelligent societies may have the technological means to annihilate themselves before they can establish contact with other civilizations or even extend beyond their native planets. As civilizations progress, they often develop technologies with profound implications for their own survival. Think of the potential for nuclear war, climate destruction, or even uncontrolled artificial intelligence. Each of these advances offers both enormous promise and serious risks. Many scholars suggest that the more advanced a civilization becomes, the greater the probability that it faces existential threats from its own creations or choices. Consequently, if self-destruction is a common destiny among intelligent species, this may explain the relative silence we perceive in the cosmos. Furthermore, if civilizations are ephemeral due to self-destruction, the window to detect their signals or for them to explore the universe is significantly reduced. The immensity of space makes it unlikely that two civilizations overlap in time and space, and this could place us in a cosmic solitude in which the echoes of civilizations that once thrived simply do not reach us. This introduces a disturbing thought. Perhaps we are rare or even unique in our ability to survive long enough to reach the stars. Ultimately, the idea of self-destructive civilizations serves as a reminder of our own precarious position in the universe. It drives us not only to consider our future technologies and their impacts, but also to reflect deeply on our values and choices as a society. If we can learn and adapt instead of repeating the mistakes of possible predecessors, we could become part of a broader galactic conversation instead of a lonely whisper in the cosmic void. The Guan bottleneck hypothesis raises a thought-provoking idea about the development of complex life on Earth and, potentially, elsewhere in the universe. It suggests that planets that harbor advanced life forms must go through a series of crucial transitions that allow their biosphere to thrive. According to this hypothesis, not all habitable environments will become ecosystems that support intelligent or technologically advanced species. This limitation raises important questions about the prevalence of life beyond our planet. Now, how does this relate to the Fermi paradox? The Fermi paradox arises from the contrast between the high probability that extraterrestrial civilizations exist in the universe and the lack of evidence or contact with such civilizations. The Gone bottleneck hypothesis can provide a potential explanation for this paradox. It postulates that, while many planets could be suitable for life, few will make the leap towards the complexity, balance, and sustainability necessary for intelligent life to arise, just as in Earth's journey, where life faced numerous challenges and mass extinctions. Other planets could also experience critical thresholds. These critical thresholds may include factors such as stable climates, the presence of water, and suitable atmospheric conditions. The hypothesis suggests that, even if life develops on many planets, conditions must align perfectly to allow intelligent life to evolve and persist. Therefore, the Gone bottleneck could indicate that intelligent life is extremely rare in the cosmos, while the universe is vast and teeming with billions of stars and potentially habitable planets. The journey from simple life forms to advanced civilizations may be fraught with obstacles that many planets simply do not overcome. This idea enriches our understanding of the Fermi paradox and leads us to contemplate the fragility of life and the extraordinary circumstances that have allowed us to exist and explore the universe. The Fermi paradox presents an intriguing dilemma. If the universe is so vast and potentially teeming with life, why haven't we found any extraterrestrial civilizations? A compelling approach to understanding this paradox is to examine the different timescales in the development of civilizations. Each civilization evolves at its own pace, influenced by a myriad of factors, including technological advancement, environmental changes, and social dynamics. Let us imagine a scenario in which a civilization arises, flourishes for a time, and then collapses or transforms into something unrecognizable. This cycle of creation and dissolution can vary greatly between different societies. Some could develop rapidly and reach advanced technologies in a few thousand years, while others could take millions of years, especially if their environment presents significant challenges. In this context, civilizations with rapid development could reach space, but they could also self-destruct rapidly before establishing lasting interstellar communication. Furthermore, let us consider the possibility that civilizations occupy only a fleeting moment in the great timeline of the cosmos. Our own civilization is relatively young, with a few thousand years in cosmic terms, which is only a blink of an eye. If most civilizations exist only briefly, the chances of coinciding in time with other intelligent species decrease significantly. This raises a thought-provoking question. Is humanity simply too early or too late to engage with our galactic neighbors? Finally, the enormous distances of space complicate things. Even if many civilizations exist, the time it takes to travel between stars or to send and receive signals is immense. A civilization may send signals to the cosmos, but if another intelligent race exists light years away and has only recently developed the ability to respond, communication would take decades or even centuries to make a round trip. Therefore, the interaction of different development timescales and the scale of the universe can create a situation in which civilizations simply do not overlap significantly, further deepening the mystery of the Fermi paradox. Fast radio bursts, or FRBs, are brief, intense bursts of radio waves from deep space that last only milliseconds but release as much energy as the sun in an entire day. These mysterious phenomena were first identified in 2007, when astronomers studying data collected by a radio telescope in Australia noticed a peculiar and powerful signal that appeared to come from far beyond our galaxy. Since that initial discovery, scientists have recorded more than 100 FRBs, and although most appear to come from distant galaxies, their exact sources remain largely unknown. This has led to some exciting theories suggesting connections to neutron stars, collapsing black holes, and even possible signals from alien technology, although no evidence of the latter has been confirmed. Interestingly, some of these bursts are repeated, meaning they have been observed numerous times from the same source, while others occur only once, adding to the mystery. The variability of their behavior has led researchers to conduct comprehensive studies with the aim of deciphering their nature and the physical processes that generate them. One of the most significant discoveries in FRB research occurred in 2019, when a team of astronomers located the exact location of a repetitive FRB in a distant galaxy. This was a revolutionary moment that allowed scientists to investigate the environment of these bursts and deepen our understanding of the universe. As research continues, FRBs offer a tantalizing vision of the unknown, opening new avenues in the field of astrophysics. Fast radio bursts, often abbreviated as FRBs, are among the most enigmatic phenomena in our universe. Astronomers detect these brief and powerful flashes of radio waves using large radio telescopes equipped with advanced technology. These bursts typically last only milliseconds, but in that fleeting instant, they can release as much energy as the sun in an entire day. The challenge lies in their sudden appearance and brevity, making it crucial for astronomers to employ sensitive and wide-ranging equipment. Most detection efforts rely on radio telescopes that can capture faint signals across vast expanses of the sky. A notable example is the Canadian Hydrogen Intensity Mapping Experiment, which has been instrumental in identifying FRBs. These telescopes are designed with wide fields of vision and high sampling rates that allow them to scan large areas quickly. When a burst occurs, it generates a characteristic signature, a distinctive pattern in the received radio waves that stands out from the universe's background noise. Once detected, these signals are typically analyzed by sophisticated computer programs. This analysis can determine properties of the bursts, such as their frequency, duration, and polarization. In addition, astronomers look for dispersion in the signal, since radio waves travel through space and encounter free electrons that delay high-frequency waves more than lower-frequency waves. This effect can help scientists measure the distance the burst has traveled and even gather clues about the environment through which it has passed. Interestingly, some FRBs are repetitive, meaning they emit additional bursts from the same source over time. This behavior offers new opportunities for study, as it allows astronomers to focus on their origins and understand the underlying mechanisms. As technology advances and more telescopes come into operation, the wonders of fast radio bursts continue to arouse curiosity and promise to reveal more mysteries about the cosmos in the coming years. The fast radio burst FRB 121102 is especially intriguing to researchers for several reasons, among which the most prominent are its unique behavior and origins. Discovered in 2011, it was the first of its kind to repeat, meaning that it emits bursts of radio waves multiple times instead of just once. This characteristic alone distinguishes it from other known fast radio bursts, which typically emit only a single pulse. This repetitive nature allows scientists to study it more closely and collect a larger amount of data. Another fascinating aspect of FRB 121102 is its origin. In 2017, astronomers located its origin in a dwarf galaxy about 3 billion light-years from Earth. This observation opened new avenues for understanding the environment and conditions that generate such energetic phenomena. Dwarf galaxies are usually less massive and have a lower star formation rate than larger galaxies, which adds an element of mystery to the processes that take place within them. The energy emitted by FRB 21102 is astonishing, with bursts containing as much energy as the sun emits in a day, but compressed into just milliseconds. This raises important questions about the physical mechanisms that drive these explosions. Researchers propose several theories, including the possible involvement of magnetars, highly magnetic neutron stars known for their explosive energy. Speculating about the formation and nature of objects that can create such dramatic bursts keeps scientists engaged and eager to explore further. The study of FRB 121102 also has broader implications for understanding the universe, as its bursts can serve as cosmic probes that allow researchers to study the intergalactic medium through which radio waves travel, helping to unlock secrets about the density and distribution of matter in the universe. Shedding light on fundamental questions of cosmology, each discovery associated with FRB 121102 not only enhances our understanding of fast radio bursts, but also contributes to the broader narrative of the cosmos. Fast radio bursts are among the most mysterious phenomena in the universe, capturing the curiosity of astronomers and cosmos enthusiasts alike. These incredibly brief flashes of radio waves last only a few milliseconds, but in that fleeting moment, they release more energy than the sun emits during its entire life. The origin of these bursts has baffled scientists since their discovery, but a compelling theory involves magnetars, a unique type of neutron star. Magnetars are neutron stars with extremely powerful magnetic fields, often 1,000 times stronger than those of typical neutron stars. To put this in perspective, if you compared the magnetic field of a magnetar to that of the Earth, it would be like comparing a small magnet to a magnet as powerful as a billion Earths. These magnetic fields of incomprehensible strength can create intense environments that give rise to spectacular physical phenomena. Researchers believe that magnetars can release immense amounts of energy by undergoing sudden changes in their magnetic fields or when they experience starquakes. These starquakes can occur when the crust of the magnetar shifts, causing convulsions that propagate through the star. During these events, the released energy can accelerate particles to near the speed of light, producing bursts of radio waves that could be detected at great distances in space. The connection between magnetars and fast radio bursts offers a tantalizing glimpse into the underlying mechanisms of the universe. While not all fast radio bursts can be attributed to magnetars, the relationship observed in several events offers a promising avenue for understanding these enigmatic signals. As research continues, we may one day unravel the entire story of fast radio bursts and accurately determine their origins among the stars. Fast radio bursts, often known by the acronym FRBs, are intense flashes of radio waves that last only a few milliseconds. While the first discovery of such bursts in 2007 surprised astronomers and raised numerous questions about their origins, the identification of repeating fast radio bursts has only increased the mystery. The importance of these repeating bursts lies mainly in their potential to reveal secrets about the universe that we are only beginning to understand. Using advanced radio telescopes, scientists have observed certain sources of fast radio bursts that emit signals multiple times. This behavior contrasts with most FRBs, which appear to occur only once and then disappear without a trace. The repeated signals suggest that the source of these bursts could be more complex and stable than was originally thought. For researchers, this consistency opens a window to unravel the mystery surrounding their origins, allowing them to collect more data and study the astrophysical environments from which these bursts emanate. In addition, these repeated bursts can provide clues about the environment surrounding their source, which is often found in distant galaxies. Repeated signals allow scientists to better analyze the materials in the interstellar medium along the path of the radio waves. By studying how these signals change or fluctuate on their journey to Earth, researchers can obtain information about the composition, density, and magnetic fields of the material in space. This knowledge enhances our understanding of cosmic evolution and the conditions present in the confines of the universe. The ongoing study of repeated fast radio bursts not only satisfies our curiosity, but also emphasizes the importance of continuous exploration in the field of astrophysics. Each new discovery related to these enigmatic signals has the potential to reshape the way we understand cosmic phenomena as scientists continue to analyze these bursts, delve into the nature of high-energy astrophysical events, bringing us closer to answering fundamental questions about the universe and our place in it. Fast radio bursts, or FRBs, are among the most remarkable phenomena in the universe, capturing the interest of scientists around the world. These brief, intense flashes of radio frequency emissions last only a few milliseconds, but can release as much energy in that short time as the sun does in an entire day. Understanding their origin involved a mixture of observation, analysis, and a bit of detective work. The scientists began by precisely locating certain FRBs in the night sky. The observations revealed that some bursts originated in distant galaxies, making them not only catastrophic events, but also fascinating clues about cosmic history. Once an FRB was detected, astronomers studied the dispersion measure, which quantifies how much the radio signal slows as it travels through cosmic material. This data helps scientists deduce how far away the explosion occurred, since more distant explosions appear more dispersed. As the investigation progressed, theories about their origin expanded. Some scientists propose that FRBs are born from cosmic cataclysms, such as collisions of neutron stars or the collapse of massive stars. Others speculate that they could be related to magnetars, highly magnetic neutron stars that emit enormous bursts of energy. The variety of theories reflects the surprisingly energetic environments in which these bursts can arise. Currently, the field of FRB research is vibrant and constantly evolving, with scientists developing new technologies to discover and study more bursts through dedicated observatories and collaborative efforts. There's hope that someday we can unravel the whole story of these cosmic mysteries, providing a deeper insight into the universe itself and its evolution. The search for knowledge about FRBs not only fuels our curiosity, but also reveals the underlying processes that govern celestial phenomena on a large scale. Fast radio bursts, or FRBs, have captured the attention of astronomers since their discovery. These short and intense bursts of radio waves originate in distant galaxies, and although their exact mechanisms remain a mystery, ongoing research sheds light on their energetic processes. Current knowledge suggests that FRBs release extraordinary amounts of energy, often comparable to that produced by our sun over several days, but emerging in milliseconds. Energy estimates for FRBs vary, but some studies suggest that each burst can release as much energy as hundreds of millions of suns. This extraordinary energy production raises important questions about the underlying sources. The main theories propose that they could be linked to events involving neutron stars, particularly magnetars, which are remnants of massive stars. Extreme magnetic fields and possible interactions with their environment could explain the immense energy and rapid release characteristic of these bursts. One of the most fascinating aspects of FRBs is their brief duration, which usually ranges from a few milliseconds to several seconds. This rapid release of energy implies a highly efficient mechanism at play. Several hypotheses have been proposed, including interactions between neutron stars, the collapse of massive star remnants, or even models suggesting they could be related to black hole mergers. Each theory has its own implications for the physics that governs these spectacular bursts. As scientists continue to collect data and refine their models, our understanding of FRBs evolves with technological advances and ongoing observational efforts. Little by little, we are getting closer to discovering the fundamental processes that generate these cosmic enigmas. The quest to understand fast radio bursts not only deepens our knowledge of the universe, but also highlights the immensity of the phenomena waiting to be explored in the cosmos. Fast radio bursts are among the most intriguing phenomena in the cosmos, standing out due to their brief and intense nature. These bursts, which last only a few milliseconds, radiate energy that can be 1,000 times more powerful than that emitted by the sun in an entire day. While radio emissions are common in space and come from various sources, such as pulsars or supernova remnants, fast radio bursts, often called FRBs, stand out for their sudden appearance and strength. The fundamental difference lies in their origin and emission patterns. Traditional cosmic radio emissions, such as those from pulsars, are relatively stable and repeatable. Pulsars produce regular pulses of radio waves as they rotate rapidly, offering a clear frequency pattern. In contrast, FRBs appear as isolated events or, in some cases, as repeated signals with variable intervals. This unpredictability makes them particularly fascinating, arousing intense interest among astronomers. Eager to explore their origins, Researchers suspect that these bursts may originate from extreme astrophysical processes. Theories suggest that they could arise from magnetars, highly magnetic neutron stars, or even from cataclysms such as neutron star collisions. As scientists analyze their signals, they have begun to uncover the underlying physics, including the environments in which these bursts occur, suggesting the complex interaction of matter and energy in the universe. In addition, the study of fast radio bursts has broader implications for our understanding of the universe, as their signals provide valuable information about the interstellar medium, the space between stars, allowing astronomers to map the structures and densities within our galaxy. As we delve into the mysteries surrounding FRBs, they continue to challenge our understanding of cosmic phenomena and ignite our imagination about the vast and unexplored mysteries of the universe. Gravitational lenses are fascinating cosmic phenomena that occur when a massive object, such as a galaxy or cluster of galaxies, deflects light from a more distant source. This deflection of light creates multiple images of that source, amplifying and distorting the light we observe. In recent years, researchers have focused their attention on how these gravitational lenses can help us study fast radio bursts, those mysterious and brief flashes of radio waves that originate in distant galaxies. Fast radio bursts, or FRBs, are intense bursts of radio frequency emissions that last only a few milliseconds. Their origin remains a mystery, but their immense energy and brief duration have motivated intense scientific research. When an FRB passes near a massive object, the gravitational lens effect can provide valuable information about both the FRB and the object acting as a lens. This interaction can enhance the FRB signal, making it detectable from much greater distances than would otherwise be possible. In addition, the study of these FRBs with lenses allows astronomers to probe the environment of the intermediate galaxy. The mass of the lens galaxy and the distribution of its matter affect how the burst is distorted and amplified. By analyzing the light and radio waves of the FB, scientists can obtain information about the structure of the lens galaxy, cosmic evolution, and the presence of dark matter, which is believed to constitute a substantial part of the mass of the universe. In addition, the variability of the observed characteristics of the FRB with lenses can reveal new information about their nature. For example, the same burst may look different when viewed through different lenses. This variability can help researchers understand the physical mechanisms that underlie these enigmatic signals, increasing our knowledge of not only the FRB, but also the cosmos itself. Therefore, gravitational lenses have become a key tool for unveiling the secrets of the universe and origins of fast radio bursts. Fast radio bursts, or FRBs, are mysterious phenomena that emit intense flashes of radio waves from distant galaxies. These bursts are fleeting, lasting only milliseconds, but their impact on our understanding of the universe is profound. One of the most exciting aspects of the FRBs is their potential as tools to study the intergalactic medium, the vast, mostly empty space full of gas and dust that exists between galaxies. When an FRB travels through the universe, it encounters various materials in the intergalactic medium. This interaction can alter the properties of radio waves, causing changes to their frequency and timing. By measuring these alterations, scientists can obtain valuable information about the density and distribution of matter through which the waves passed. Each FRB carries a unique footprint of its journey through the cosmos, revealing the conditions of the intergalactic environment. Researchers can use data from multiple FRBs to build a more complete map of the intergalactic medium. This is especially important, since the medium itself is difficult to observe directly. The dispersion or propagation of radio waves provides clues about the electron density in different regions. This helps scientists understand how matter is distributed and how galaxies interact with their environment over cosmic time. The study of FRBs also raises questions about the evolution of the universe itself. As we explore these explosions, we gain information about the large-scale structure of the cosmos and how it has changed over billions of years. In this way, These fleeting signals are not only strange phenomena, but also serve as powerful tools to unravel the hidden complexities of the universe around us. Rogue planets are fascinating celestial objects that roam the cosmos completely separate from any stellar system. Unlike conventional planets that orbit a sun and obtain heat and light from their parent star, rogue planets float freely in the vast void of space. It is believed that these planets originated in a solar system, but were expelled into the interstellar medium due to interactions with other large celestial bodies or violent events during the formation of their stellar systems. The characteristics of rogue planets can vary significantly. They can range in size from something similar to Earth to massive giants much larger than Jupiter. Some may have atmospheres and geological characteristics similar to those of traditional planets, while others may be cold, dark, and covered by thick layers of icy material. This variability raises intriguing questions about their formation and evolution. Scientists theorize that some could have formed in isolation, while others could have been part of larger systems before being expelled. The conditions on rogue planets can be quite extreme. Without the heat and light of a nearby star, these planets are mainly cold and temperatures can drop to levels that we cannot easily understand. But there's a touch of mystery surrounding these planets. Some researchers suggest that rogue planets could harbor hidden oceans under the surface, kept warm by geothermal activity, suggesting the possibility of life in the most unexpected places. The discovery of rogue planets has expanded our understanding of planetary systems and the dynamics of the universe. Recently, astronomers have identified thousands of these worlds, revealing a thriving population in the dark expanses of space. Each rogue planet reminds us of the complexity of our universe and leads us to reflect on the countless possibilities of celestial life and the nature of planets themselves, which awakens the imagination and inspires new explorations. Rogue planets are fascinating celestial bodies that move through space without being attached to any star. These planets are often difficult to detect, as they do not emit light of their own. Instead, scientists use various indirect methods to detect them, relying on techniques that reveal their faint presence in the immensity of space. One of the main methods involves the gravitational microlensing technique. This process occurs when a rogue planet passes in front of a distant star, temporarily deflecting and amplifying the light from that star due to the planet's gravity. By observing a sudden brightening of the star, astronomers can deduce the presence of the rogue planet. This method can reveal planets that are incredibly far away, even in regions of space where they could exist alone, far from their original stars. Another strategy is to perform infrared observations. Rogue planets, despite not shining brightly, emit some thermal energy, especially if they are young and still cooling. Instruments such as the Wide-Field Infrared Survey Explorer, or WISE, can detect their thermal footprint by scanning the skies for these faint heat emissions. Scientists can identify possible rogue planets hiding in the cosmic shadows. Finally, astronomers also take into account the gravitational influence of rogue planets on other celestial bodies. These planets can affect the orbits of nearby stars or asteroids, leading to unusual patterns that indicate their existence. By gathering these clues, scientists are gradually discovering the elusive population of rogue planets that roam our galaxy, offering information about their formation and the dynamics of our universe. Rogue planets, those celestial vagabonds who venture alone into the vastness of space without being linked to any star, have fascinated astronomers for some time. Several theories attempt to explain how these enigmatic worlds arise. One prominent idea suggests that rogue planets could form in the same way as traditional planets, accumulating mass in a protoplanetary disk around a young star. However, unlike their counterparts bound to a star, some of these planets could be ejected from their orbits through gravitational encounters, perhaps with a larger planet or a passing star, launching them into the void of interstellar space. Another formation mechanism highlights the possibility of collapse scenarios in gas clouds in regions of space where gas and dust merge. Local instabilities could trigger the collapse of a section of this material, leading to the birth of a planet directly from the cloud. This process could lead to rogue planets that never had the opportunity to be dragged by the gravity of a star or that formed completely independently of any solar system. Despite lacking a host star, these young worlds could still show characteristics similar to those of other planets. Interestingly, some astronomers speculate that rogue planets could be remnants of planets that have been torn from their stellar systems. This scenario could occur in densely populated star clusters, where gravitational interactions are more common over time. These interactions could cause planets to be dragged out of their original systems, becoming transient, wandering beings in the galaxy. The study of vagabond planets is rapidly evolving, and although the formation mechanisms are still being refined, each theory that is added to our knowledge expands the tapestry of our cosmos. When we look at the stars, the existence of these solitary giants reminds us of the dynamic processes governing the universe, constantly reshaping and stirring this celestial crucible. Vagabond planets, those intriguing worlds that wander alone through the cosmos without being tied to a star, are more common than many imagine. Estimates suggest that there could be billions of these planets floating freely in our galaxy, the Milky Way. In fact, some studies propose that there may be more vagabond planets than stars in the galaxy, a truly amazing idea given the number of stars we observe. It is believed that vagabond planets form during the chaotic initial stages of planetary system development. During this time, interactions between the planets in formation and their progenitor stars can cause expulsions that cause some planets to be thrown into the interstellar void. This process can occur in binary systems or dense star clusters where gravitational forces alter planetary orbits. One of the most fascinating aspects of vagabond planets is their potential to harbor life, even without the heat of a nearby star. Some of these planets could possess an underground ocean kept liquid by internal geothermal energy. There is even a small possibility that conditions allow for the existence of microbial life that thrives in the darkness under a thick layer of ice. As telescopes and detection methods improve, astronomers continue to search for more wandering planets scattered throughout the galaxy. Each discovery increases the understanding of these elusive wanderers, revealing the diverse and complex nature of our universe. The idea that countless planets lurk in the immensity of space, silently navigating the galaxy, invites us to reflect on the possibilities of our cosmic neighborhood. The largest known wandering planet is called PSOJ 3185-22 and is fascinating in its nature. Unlike many planets that orbit stars, PSOJ 3185-22 wanders through space independently. Not being tied to any star, this planet has a mass approximately 6 times greater than that of Jupiter, making it one of the most massive wandering planets identified to date. Its enormous size and its solitary journey through the cosmos offer a unique vision of the processes of formation and planetary evolution. Discovered in the year 2013, the identification of SOJ 3185d22 occurred through the study Pan-STARRS 1, an astronomical study project based in Hawaii. This project employs advanced telescopes to capture images of the night sky and identify various celestial objects. As the researchers analyzed the data, they observed a faint moving object that appeared to change position against the backdrop of distant stars. This unusual movement was a key indicator that it was not a traditional star or galaxy, but a wandering planet. Subsequent observations revealed that the planet has a temperature of around 1,000 degrees Celsius, indicating that it likely has a dense, gaseous atmosphere. This atmosphere shows the presence of clouds and may even hide fascinating meteorological systems. PSOJ 3185-22 is located about 83 light-years from Earth. Its proximity and characteristics allow scientists to study it in more detail, deepening our understanding of freely floating planetary bodies. The discovery of wandering planets like PSOJ 3185-22 raises intriguing questions about the formation of planetary systems. It challenges the traditional view that planets must orbit stars to exist and suggests that our universe is full of orphaned worlds adrift in the void. Each discovery adds a piece to the puzzle of how planets, stars, and galaxies interact in the vast expanse of space. Wandering planets are fascinating celestial bodies that wander through the cosmos without being linked to a star. These planets, which have been expelled from their original stellar systems, depend on different processes to retain heat and avoid plunging into freezing temperatures. Instead of extracting energy from a sun, which would be impossible for them, they generate heat through their own internal mechanisms and the residual heat from their formation. When a planet forms, it accumulates mass from the gas and dust of a protoplanetary disk. During this process, kinetic energy is converted into thermal energy, resulting in significant initial heat. Although wandering planets can drift for millions or billions of years, they often retain some of this primordial heat. This is especially true for larger planets, as they possess greater gravitational pressure that slows the rate of heat loss. In addition, some wandering planets may undergo radiogenic heating, a process that involves the disintegration of radioactive isotopes within their causative elements, such as uranium and thorium, which naturally disintegrate, releasing heat that can significantly prolong the heat of these solitary giants. This internal source of heat can be crucial to maintaining any potential geological activity, which in turn could create a more hospitable environment for the possibility of life, albeit in very different ways than planets orbiting stars. In addition, it is intriguing to consider that some wandering planets may have atmospheres, trapped gases, and even ice. These components could help insulate the planet, retaining heat and preventing it from radiating into the cold immensity of space. The mystery and intrigue surrounding these solitary wanderers of the galaxy challenge our understanding of planetary formation and evolution, while arousing our curiosity about the potential for life in the most unlikely places. Wandering planets, those that wander through space without a mother star, present a fascinating, if enigmatic, possibility for life. Wandering planets, unlike those found in a solar system, move freely through the cosmos, often subjected to extreme temperatures that may seem inhospitable at first glance. However, scientists theorize that, under certain conditions, life could arise even in these cold and dark environments. One intriguing idea suggests that wandering planets could possess underground oceans. Geothermal heat from the interior of the planet could create warm pockets under its icy crust, allowing for the existence of liquid water. Water is often referred to as a fundamental ingredient for life, and if conditions are favorable, microbial life could thrive in these hidden oceans. This life form could depend on chemosynthesis, an alternative metabolic process that uses chemical reactions instead of sunlight as an energy source. Another factor that could favor life on these planets is the presence of complex organic molecules. Research indicates that these necessary building blocks could form in the hostile environments of the solar system. If wandering planets were once part of the solar system, they may have retained some of these essential compounds even after losing their stellar source of heat and energy. The versatility of organic chemistry suggests that life, as we know, it could evolve in surprising ways in different environments. Although the notion of life on wandering planets remains speculative, it awakens the imagination and encourages scientists to extend their search beyond traditional habitats. The search for the understanding of these solitary and anchorless worlds not only challenges our definitions of life, but also invites us to explore the vast hidden possibilities between the stars. For now, the idea that life can persist in the shadowy depths of a wandering planet is a tempting frontier in the search for extraterrestrial existence. The wandering planets, those solitary vagabonds that move through the cosmos without being united to any star, can significantly influence in the dynamics of the stellar systems with which they meet, since these planets move away from their original systems and carry with them immense gravitational forces. When a wandering planet approaches a stellar system, its gravity can alter the orbits of planets within that system. This interaction can lead to a cascade effect, in which the orbits of entire planets are altered, possibly expelling smaller celestial bodies from their orbits or even causing collisions. The gravitational influence of a wandering planet is not uniform. It can vary a lot depending on the size of the wandering planet and its relative speed when passing through the stellar system. If the wandering planet is especially massive, like a gas giant, its impact could cause significant disturbances that could lead to the destabilization of the orbits of other planets. This could allow smaller terrestrial planets to be thrown into the cold darkness of space, forever losing the heat from their stars. In addition, the interactions between a wandering planet and the stars of the system can create opportunities for new formations. Some scientists postulate that the passage of a wandering planet can facilitate the capture of other celestial bodies, like asteroids or comets, which would lead to the creation of new moons or rings around the existing planets. This means that, instead of causing havoc alone, the wandering planet could also contribute to the construction of new planetary systems. While wandering planets may seem like dangerous instigators in a universe's great dance, they also add layers of complexity and intrigue to cosmic relationships. Their solitary journeys and their gravitational whispers remind us that the universe is full of unpredictable actors, each of which influences the great tapestry of existence in ways that we still strive to understand. Wandering planets and interstellar objects like Oumuamua offer a fascinating vision of the cosmic landscape. The wandering planets are celestial bodies that do not orbit around any star, but rather drift through the immensity of space, without ties or bonds, often expelled from their original stellar systems due to gravitational interactions. It is estimated that there could be billions of wandering planets in our galaxy alone. These wandering worlds tend to be elusive, which makes their detection difficult, but their mere existence suggests a dynamic and often chaotic cosmos. On the other hand, interstellar objects like Oumuamua are a different type of traveler. These are materials that come from outside our solar system and enter it for a brief, fleeting visit. Oumuamua, discovered in 2017, became famous for its unusual shape and rapid movement. Unlike wandering planets, which can be entire worlds, interstellar objects can be much smaller and vary in their composition, being able to be from icy comets to rocky remains, sharing the intriguing characteristic of being cosmic messengers from other stellar systems. The connection between these two focuses on their journey through space. Wandering planets, like interstellar objects, are representative of how dynamic and interconnected our universe is. Both can offer clues about the formation and evolution of planetary systems and the destiny of celestial bodies. For example, the existence of wandering planets challenges our understanding of how planetary systems develop and survive, since they can transport materials and elements through great distances, potentially influencing the formation of new stars and planets along their trajectories. Both wandering planets and interstellar objects are reminders of the mysteries that hide beyond our solar system. As we study them, we delve into our understanding of the cosmos, revealing not only the nature of these bodies, but also shedding light on the processes that shape the very fabric of our universe. Each observation opens new avenues of investigation, awakening our curiosity for what is beyond the stars we know. Wandering planets, celestial bodies that wander through space without a star to call home, serve as fascinating vehicles for the distribution of organic compounds through the galaxy. These planets, which are formed in a similar way to normal planets, but that are finally expelled from their solar systems, can transport complex molecules like amino acids and simple sugars as they move through the immensity of space. These organic compounds survive the harsh conditions of the universe, including the extreme temperatures and the radiation, largely due to their protection of the elements of the subsurface of the planet. As the wandering planets travel between galaxies or within the confines of a galaxy, they can collide with comets, asteroids, and other celestial bodies, which can lead to the exchange of organic material. If these interactions occur, they can effectively sow new worlds with the potential to propagate life, scattering the basic components of organic chemistry through light years of space. This capacity to transport precursors of life adds an intriguing layer to the idea of panspermia, the theory that life, or the necessary components for life, could be distributed throughout the universe by natural cosmic means. In addition, the atmospheres of wandering planets can play a role in this distribution, since many could have retained some atmosphere, even if thin, that could contain traces of organic chemical substances produced by geological or extraterrestrial processes in certain conditions, such as volcanic activity or chemical reactions. These compounds could be released into space, contributing even more to the galactic set of organic materials. Interestingly, the existence of wandering planets could also affect our understanding of life beyond Earth. If these planets can transport the appropriate components through the galaxy, new possibilities open for the appearance of life in places we would not have initially considered. The alone to think that life could be traveling on a wandering planet, sharing its history with countless celestial bodies, which enriches our perspective on the cosmic tapestry of the potential of life. The next time we reflect on the mysteries of the cosmos, it is worth considering these enigmatic wandering planets and their potential as cosmic messengers of life. Cosmic voids are fascinating regions of space that intrigue astronomers and cosmologists. They are vast expanses where the density of matter is significantly less compared with the average density of the universe. Think of them as the gaps in the cosmic web, the large-scale structure of a universe formed by filaments, clusters, and superclusters of galaxies. While most of the universe is dotted with galaxies and clusters, these voids can extend over tens of millions of light years with very few galaxies, or even none. All these voids are defined by their size and the density of the matter they contain. Generally, a cosmic void is characterized as an area that has a density of galaxies much less than the general cosmic average. A common threshold is that a cosmic void has at least 30 to 50% less density of galaxies than the surrounding regions. Some of the largest voids can reach up to 100 million light-years in diameter, making them some of the emptiest regions of the observable universe. The formation of cosmic voids is a key aspect to understanding the evolutionary history of the universe. It is believed that they originated from density fluctuations in the early universe, where regions of slightly lower density allowed matter to separate and form the filaments and clusters that make up galaxies over billions of years. The gravitational effects from nearby matter have caused these voids to expand as galaxies cluster, leaving behind significant distances of empty space. The study of cosmic voids not only helps astronomers map the large-scale structure of the universe, but also sheds light on dark energy and the expansion of the universe. By examining how galaxies exist on the boundaries of these voids, scientists can learn more about the intricate dance of matter throughout the vast cosmos. So, although they may seem empty and insignificant at first glance, cosmic voids play a crucial role in our understanding of the universe's past, present, and future. Detecting and mapping them is a fascinating endeavor that depends on understanding the vast and intricate architecture of the cosmos. Cosmic voids are the enormous, largely empty spaces between filaments of galaxies that together create a cosmic web-like structure. To discover these voids, scientists employ a multifaceted approach combining advanced technology with the principles of light and gravity. One of the main tools for detecting cosmic voids is large-scale galaxy surveys. Observatories around the world, equipped with powerful telescopes, systematically scan the night sky to catalog millions of galaxies as they collect data. Scientists analyze how galaxies are distributed throughout the universe. In a typical scenario, these galaxies are grouped into filaments, leaving significant gaps, or voids. By statistically examining these distributions, researchers can identify areas where galaxies are sparse, indicating the presence of voids. Gravitational lenses also play a key role in this exploration. When light from a distant galaxy passes near a massive object, such as a cluster of galaxies, the light bends due to gravity. Scientists can measure this curvature effect to infer the distribution of mass throughout the universe. By understanding where mass is concentrated and where it is missing, they can locate and trace the boundaries of these voids with greater precision. This technique allows scientists to explore cosmic structures even when direct observations prove difficult. Another innovative method involves computer simulations that model the universe's evolution. These simulations help scientists predict where voids are likely to form based on the laws of gravity and the distribution of matter. By comparing these simulations with real observational data, they can refine their models and improve the accuracy of void mapping. Through these various methods, researchers continue to unravel the secrets of cosmic voids, revealing not only their location, but also their implications for understanding dark energy and the ultimate fate of our universe. The largest known cosmic void is the Boötes void, which extends about 330 million light-years. This enormous extension is a kind of enigma in the universe, since it contains very few galaxies, so few that it constitutes one of the most significant voids in our cosmic structure. Surprisingly, there are only about 60 galaxies in this vast region, a stark contrast to other regions of space that can house thousands of galaxies in similar volumes. The discovery of the Boötes void dates back to the late 20th century, when astronomers began conducting extensive sky surveys. It gained more attention when a dedicated team of researchers was mapping the distribution of galaxies as part of a broader effort to understand the structure of the universe through detailed observations. These astronomers located this unusual void and observed its extensive emptiness and the strange arrangement of galaxies that appear to accumulate on its periphery. The existence of such voids is significant as it challenges our understanding of how matter is distributed throughout the universe. These voids are regions where the density of matter is much lower than average, helping to provide valuable insights into the evolution of the universe and how cosmic structures form. The Boötes void in particular provides a sharp visualization of the cosmic web where galaxies are interconnected by filaments and clusters, leaving large areas completely devoid of matter. Interestingly, the existence of the Boötes void raises compelling questions about dark energy and dark matter. As researchers continue to study these cosmic phenomena, they learn more about the fundamental forces that shape our universe. Each new piece of information about voids helps astronomers refine their models and deepen their understanding of the cosmos, making the study of voids an essential frontier in cosmology. Cosmic voids are fascinating regions of space that play an important role in our understanding of the universe's large-scale structure. These vast, almost empty expanses make up around 80% of the universe, in contrast with the densely populated areas where galaxies cluster. When astronomers map the cosmos, they discover that galaxies are not randomly scattered, but tend to cluster along filaments, creating a network-shaped pattern full of these voids. The large-scale structure of the universe can be visualized as a cosmic tapestry. Galaxies cluster into filaments that are the threads of this tapestry. Between these filaments are the cosmic voids that, although sparse, significantly influence the overall dynamics of cosmic evolution. Understanding how voids form and their relationship to galaxy formation sheds light on how matter clusters and the fundamental forces involved in the universe's expansion. Interestingly, voids can affect the behavior of galaxies. The gravitational influence of surrounding matter can attract galaxies to the edges of these voids, creating intriguing patterns in the distribution of galaxies. The voids themselves can be seen as regions where gravitational forces are weaker, allowing the study of cosmic acceleration. Scientists investigate how these empty spaces contribute to the expansion of the universe, offering information on phenomena such as dark energy. This interaction between cosmic voids and galactic filaments reveals much about the formation and structure of the universe, reminding us that, on the grand scale of the cosmos, emptiness is as important as density. The distribution of cosmic voids not only enriches our understanding of how galaxies are organized, but also highlights the scale and depth of the mysteries of the universe that await exploration. Dark energy plays a fascinating role in the great tapestry of the universe, especially with regard to the formation and even the evolution of cosmic voids. To begin, let's understand what cosmic voids are. They are vast regions of almost empty space that contain very few galaxies compared to the most densely populated areas known as galaxy clusters. These voids are a crucial part of the large-scale structure of the universe, since they constitute a significant portion of it. As the universe has expanded, dark energy has been a driving force behind this acceleration. Initially, the universe was dominated by gravity, which attracted matter and enabled the formation of galaxies. However, as it expanded, a mysterious form of energy, dark energy, began to assert its influence. This energy is believed to constitute about 70% of the total energy content of the universe and exerts a repulsive force that separates galaxies and causes the dispersion of matter throughout the cosmos. This dynamic interaction creates and sustains the voids, while galaxies cluster under the influence of gravity. Dark energy creates conditions that allow these clusters to separate as space expands. Regions that were previously densely populated may become less so, leading to the formation of voids where few galaxies exist due to the continued influence of dark energy. These voids have the potential to grow over time, becoming larger and emptier as the surrounding galaxies are pushed outward. Interestingly, the evolution of voids is influenced by the distribution of cosmic matter and the rate of cosmic expansion. Over billions of years, voids can evolve from being mere depressions in the cosmic web to becoming expansive regions that are largely devoid of matter. This interaction between dark energy and cosmic structure not only helps explain the current observed distribution of galaxies, but also sheds light on the nature of dark energy itself. Its enigmatic properties remain a subject of research and awe within cosmology. Cosmic voids are expansive, almost empty regions of space that constitute about 80% of the volume of the universe. Despite their immensity, they contain very few galaxies, making them a fascinating puzzle in cosmology. Understanding these voids challenges existing theories about galaxy formation, as they contradict the idea that galaxies should be evenly distributed throughout the universe. Instead, we find that galaxies often cluster around denser regions, leading scientists to rethink how they develop under different conditions. Initially, it was thought that they formed uniformly in the early universe, following a process largely driven by gravity. However, the existence of cosmic voids suggests that larger gravitational influences may be at play in these sparsely populated areas. The lack of significant matter results in weaker gravitational attraction that can hinder the formation of new galaxies. The question arises as to whether galaxies are emerging from denser regions and what processes allow them to exist in the rarefied spaces of voids. Researchers are exploring the role of dark matter and dark energy in this context. Dark matter, which is invisible and interacts primarily through gravity, could create a network that favors galaxy formation in denser regions, leaving the voids relatively barren. Interestingly, the nature of dark energy, which influences the expansion of the universe, could affect how galaxies move and form over cosmic time. This interaction between different types of matter invites a more nuanced understanding of how cosmic structures evolve. The study of cosmic voids not only helps us refine our models of the universe, but also reveals fundamental insights into its composition and destiny. Voids are a reminder that, in the grand design of the universe, emptiness can be as significant as density. By observing these enigmatic areas, scientists hope to discover the underlying mechanisms that govern galaxy formation and, in turn, improve our understanding of the cosmos itself. Vacuum polarization is a fascinating phenomenon in cosmology and astrophysics. In essence, it describes the effects of matter and energy interactions in the vast emptiness of space, known as cosmic voids. These voids are immense regions of space with significantly fewer galaxies and matter compared to the more densely populated areas within it. Vacuum polarization refers to how cosmic structures influence the behavior of light and matter in these sparsely populated areas. This phenomenon is vital to our understanding of how the universe evolves, as light traveling through these voids can be affected by the gravitational attraction of any surrounding matter, which can alter its trajectory and even its properties. This means that vacuum polarization has important implications for our observations of the cosmos, especially in terms of how we interpret distant galaxies and the cosmic microwave background radiation, the remnants of the Big Bang that fills our universe. In addition, vacuum polarization plays a crucial role in mapping dark energy and its effects on cosmic expansion. By studying how light is influenced in these voids, scientists can gain information about the underlying structure of the universe and the mysterious forces that govern its expansion. Vacuum polarization helps cosmologists refine their models of the universe, leading to a deeper understanding of phenomena previously shrouded in mystery. Understanding vacuum polarization allows researchers to unravel the layers of cosmic structure formation as they discover how these voids interact with light and matter and gather vital clues about the history of the universe, including the role of dark matter and dark energy in shaping the cosmic landscape. This knowledge enriches our overall understanding not only of the voids themselves, but also of the entire universe, highlighting the elegant interaction between light, matter, and the cosmos. Cosmic voids are vast, almost empty regions of the universe that can span hundreds of millions of light years. These voids are important because they influence the distribution of matter that shapes the large-scale structures of the cosmos. Although we often focus on galaxies and stars, it is fundamental to understand that these voids represent about 80% of the volume of the universe. Their presence helps determine where matter clusters and where it is scarce. The effects of cosmic voids on the distribution of matter are profound in the areas surrounding them, where we find dense clusters of galaxies, filaments of dark matter, and other cosmic structures influenced by gravity. Galaxies tend to cluster along the edges of voids, attracted by the gravitational force of their more massive neighbors. The space within these voids fosters a unique environment where matter is less densely packed. This balance between gravity attracting matter and the vast emptiness of voids creates a cosmic web of galactic structures and space where less matter exists. In addition, cosmic voids influence the behavior of light as it travels through the universe. The lower density means that light can travel through voids with less distortion compared to regions filled with galaxies. This also means that voids play a role in how we perceive the universe. For example, when we observe distant galaxies, we may see their light less curved in these empty regions, allowing us to get a clearer view of the cosmos. Interestingly, research continuously studies voids to learn more about dark energy and the expansion of the universe, since cosmic voids are large areas of low density that can provide information about how the expansion of the universe is accelerating by examining the dynamics of matter in relation to the voids. Scientists hope to unravel more mysteries about our expanding universe, leading to a deeper understanding of its composition and the forces at play. The study of cosmic voids offers a unique window into the conditions of the early universe. Cosmic voids are large, empty spaces between galaxy clusters. Surprisingly, these voids make up about 80% of the universe's volume. Their existence is not only a backdrop for the most populated regions full of galaxies, but they contain clues to understand how the universe evolved over billions of years in the early universe. After the Big Bang, matter was distributed relatively uniformly, but over time, small fluctuations in density began to emerge. Gravity attracted matter and led to the formation of structures such as galaxies, clusters, and these cosmic voids. By examining the size, shape, and distribution of the voids, researchers can deduce the speed at which matter clumped together during the early stages of expansion of the universe. This process of clumping is directly related to fundamental questions about the nature of dark matter and dark energy, which influence cosmic structure. Interestingly, the study of the voids also illuminates the history of cosmic expansion, since galaxies and clusters, when forming, affected the surrounding space, creating regions where matter was scarce. The characteristics of the voids, such as their average size and how they grow, can reveal the universe's expansion rate over time. By modeling these voids, scientists can extract data that narrates the expansion of the universe from its infancy to its current state. The analysis of cosmic voids allows scientists to reconstruct a more complete picture of the early universe. Each void tells a story of how matter behaved under the influence of gravity and expansion during those formative years. This understanding not only helps map the current structure of the universe, but brings us closer to unraveling the mysteries that shaped everything we see around us. Cosmic voids are vast, empty spaces in the universe where very few galaxies are found. They are surrounded by denser regions, such as galaxy clusters and filaments. These structures are part of the cosmic web, a framework that defines the distribution of matter in the universe. While voids may seem inert at first glance, they play a crucial role in the dynamics of the cosmos, since galaxies and clusters of galaxies gravitate towards each other, attracted by the force of gravity, and interact with the surrounding voids in distinct ways. The gravitational influence of nearby clusters can affect the movement of galaxies within the voids. When galaxies move away from these dense regions toward the center of the voids, they can create interesting phenomena. For example, their trajectories can be influenced by the mass of the surrounding structures, even when they are not in direct contact. In addition, research has shown that voids can also affect the behavior of dark matter and dark energy within the universe. These empty regions can alter the gravitational attraction exerted by the clusters, leading to unique patterns of movement and separation. Evidence suggests that galaxies on the edges of these voids tend to accelerate away from the gravitational forces of their denser neighbors. This interaction helps paint a more complex picture of how matter is distributed and how structures evolve over cosmic time. In addition, voids can foster the formation of new galaxies. As matter gradually inhabits these empty spaces, gas and dust can begin to accumulate, giving rise to the birth of new stars and galaxies. This aspect makes voids not only empty places, but also essential components in the narrative of ongoing cosmic evolution, contributing to the rich tapestry of the universe that we observe today. The discovery of the accelerated expansion of the universe emerged from a fascinating combination of evidence collected over the years, which fundamentally altered our understanding of cosmology. In the late 20th century, astronomers were studying distant supernovas, in particular, a type known as Type I supernovas. These stellar explosions can serve as reliable markers for measuring cosmic distances, as they have a consistent brightness. Observations of these explosions revealed something unexpected in the mid-90s. Two independent teams of researchers, known as the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to use these supernovas as standard candles to measure the rate at which the universe is expanding. They discovered that, instead of slowing down due to gravity, the expansion of the universe was accelerating. This surprising revelation arose by comparing the brightness of supernovas that were billions of light years away with those that were closer to home. The farther away the supernovas were, the fainter they appeared, indicating that they were farther back in time. The data suggested that the rate of expansion is increasing over time, which puzzled scientists for several reasons. One of the main explanations for this acceleration is a mysterious force called dark energy, which is believed to consist of approximately 70% of the universe. This finding also raised new questions about the nature of gravity and how it interacts with the cosmos as a whole. The implications of this discovery have been profound. It has not only reshaped our understanding of cosmic history, but has also led to a deeper investigation of the fundamental structure of the universe. The understanding that an invisible force pushes galaxies outward has captivated both scientists and enthusiasts, expanding the limits of our understanding of physics and the fate of the universe itself. Through the lens of these distant supernovas, we have begun to unravel a cosmic mystery that continues to intrigue us. The Big Bang Theory has long been our best explanation of the origin and evolution of the universe. It describes how the universe began from an incredibly hot and dense state and has been expanding ever since. However, in the late 20th century, a surprising advance in our understanding emerged: the accelerated expansion of the universe. This phenomenon not only challenges our perceptions, but also raises deeper questions about the very structure of our cosmos. Initially, scientists believed that gravity would cause the expansion of the universe to slow. Over time, however, observations, particularly those of distant supernovas, revealed something unexpected. Instead of slowing, the rate of expansion is increasing. This acceleration suggests that some mysterious force is separating the universe, a phenomenon we now refer to as dark energy. This discovery introduces a level of complexity that the original concept of the Big Bang did not take into account. Dark energy presents profound implications for our understanding of the fate of the universe. If this acceleration continues, it could lead to a scenario known as the Big Freeze, in which galaxies move farther and farther away until the stars eventually go out, creating a chilling vision of an ever-expanding universe that may lose its ability to sustain life as we know it. Such results compel us to reconsider key elements of the Big Bang Theory and rethink cosmic evolution's dynamics. Thus, while the Big Bang Theory provides a solid basis for the origins of the universe, the discovery of its accelerated expansion challenges us to expand our concepts and encourages scientists to explore innovative ideas about the forces that act in the universe. As we continue to collect evidence and refine our models, we are slowly approaching a deeper understanding of the cosmos and our place in it. This journey is not only about answering questions, but also about appreciating the complexity and wonder of the universe we inhabit. Dark energy plays a crucial role in the accelerated expansion of the universe. It is a mysterious force that seems to permeate all space and represents about 70% of the total energy content of the universe. This enigmatic form of energy is fundamentally different from the matter and radiation with which we are familiar. While these traditional forms of energy tend to bring things together through gravity, dark energy has the opposite effect and separates galaxies. Discovered through observations of distant supernovas in the late 1990s, dark energy was unexpected. Astronomers noticed that, as they looked deeper into space, they observed that the universe was not only expanding, but that this expansion was occurring at an increasing rate. This observation led to the conclusion that some form of energy must be driving this acceleration, and thus dark energy was born as a concept in cosmology. Scientists hypothesized that dark energy could be a property of space itself or related to a more complex field that extends throughout the universe. As space expands, more of this energy appears, creating a kind of cosmic thrust. To explain it better, imagine the universe as a balloon. As the surface of the balloon stretches, it creates more area without the need for additional material, much like dark energy could act in our universe. Understanding dark energy remains one of the most important challenges in modern astrophysics. Researchers are not only trying to measure its properties, but also to understand its nature. Various experiments and astronomical studies, such as those carried out by the Hubble Space Telescope, try to unravel this cosmic mystery. As scientists delve deeper, they hope to discover more about this force that shapes the destiny of our universe. Dark energy is one of the most enigmatic aspects of our universe and plays a crucial role in its expansion. Think of it as a cosmic agent that separates galaxies at an accelerated rate. The prevailing model, known as the cosmological constant, predicts that this energy is uniform and immutable throughout space and time. If this model is true, the universe will continue to expand forever, leading to a future known as the Great Freeze, in which galaxies move away from each other and the stars eventually go out, leaving a vast, cold, dark void. However, not all scientists agree with the role of the cosmological constant. Other dark energy models propose various dynamics. For example, some suggest that dark energy could evolve over time, changing its influence as the universe ages. These possibilities could lead to dramatically different futures compared to the steady-state model. In some scenarios, dark energy could increase in strength, which could cause the universe to tear apart in a phenomenon known as the Big Rip. Even more fascinating are the models that involve interactions between dark energy and matter. Some theories speculate that dark energy could gradually decrease, slowing the rate of expansion and eventually stopping it. This scenario could lead to a more stable universe that could culminate in a second phase of collapse, sometimes called the Big Crunch, in which everything converges back into a singular point. These different models underscore the importance of ongoing astronomical observations by studying the cosmic microwave background radiation, the galactic distributions, and the properties of distant supernovas. Scientists continue to gather clues about the true nature of dark energy. Understanding how these models could shape the future of the universe is not only a search for knowledge, but also a journey to the heart of existence itself. The cosmic coincidence problem arises from a disconcerting observation at the heart of modern cosmology. For much of the history of the universe, expansion was mainly influenced by the gravitational attraction of matter, which slowed it down. However, about 7 billion years ago, something extraordinary happened. The universe began to accelerate in its expansion, mainly due to a mysterious force called dark energy. This change raises a fascinating question. Why is the moment when these two processes occur, the density of matter and the density of dark energy, so closely aligned in the current universe? To understand it, we must first consider the scales involved. The universe is approximately 138 billion years old. If we imagine the development of cosmic structures over this time, we find that the matter that contributes to gravitational attraction has dominated the dynamics of the universe for most of its life. Only in the more recent past did dark energy, an invisible energy that fills space uniformly, begin to dominate and accelerate the expansion of the universe. The cosmic coincidence problem asks why these two forces, which have profoundly different effects on cosmic evolution, seem to be finely balanced at this critical juncture. A compelling perspective is that we are observing the universe at a unique moment. If cosmic evolution had transpired differently, our planet might have formed in a universe where dark energy dominated from an earlier stage, or perhaps in one in which matter continued to dominate much longer. The conditions necessary for life, as we know it, depend on this precise moment. This concept is often known as the anthropic principle, which suggests that the fundamental features of the universe are conditioned in part by the existence of observers like us. The question of the cosmic coincidence problem remains open, inviting researchers to explore theories that can explain this fortuitous balance. Some suggest modifications to our understanding of gravity or propose completely new physics. In any case, contemplating these ideas not only deepens our understanding of cosmic evolution, but also highlights the profound mysteries that continue to define the universe we inhabit. As we delve into these cosmic questions, the story of our universe becomes even more inspiring. Modified gravity theories offer intriguing alternatives that aim to explain the accelerated expansion of the universe without resorting to dark energy. Traditional cosmological models involve dark energy, a mysterious force believed to constitute a significant part of the universe and responsible for its acceleration. However, scientists have sought different approaches based on adjustments to the prevailing understanding of gravity itself. A prominent theory is called modified Newtonian dynamics, or MOND. This theory revises Newton's laws to explain the phenomena observed in the galaxies that cannot be completely explained by the visible matter by itself. By modifying the functioning of gravity at great distances, MOND proposes that the dynamics of the objects in the galaxies can reveal a different relationship between the mass and the gravitational effects. As a result, this theory provides insight into the behavior of the universe without resorting to invisible dark energy. Another key competitor is the F-R gravity models. In these frameworks, the law of gravity is modified by changing the way we interpret the curvature of space-time by altering the function related to the density of matter and energy in the universe. These models suggest that gravity itself behaves differently at cosmic scales, offering a way to explain the accelerated expansion and suggesting our current understanding of gravity may be incomplete. Finally, there are theories such as the DGP model, which introduces a concept of gravity in 5 dimensions. Here the universe is conceived as if it had a hidden dimension that changes the way gravity works on a cosmic scale. These models provide information on how gravity can vary in intensity depending on the distance, which could explain the accelerated expansion of the universe in a way different from dark energy. Through these modified theories, scientists continue to deepen our understanding of the cosmos, revealing the rich complexity of gravitational interactions. The term Hubble tension refers to the ongoing debate among astronomers about the rate at which the universe expands. This rate is measured by the Hubble constant, which quantifies how quickly galaxies recede from us due to the expansion of space itself. The intrigue arises because two different methods of measuring this constant have yielded contradictory results. One of the methods is based on the observation of the cosmic microwave background radiation, the remnant light of the Big Bang, while the other involves direct measurements of nearby galaxies. The discrepancy is not trivial. An approach based on observations of the early universe through satellites, such as the Planck spacecraft, suggests the Hubble constant is about 69 kilometers per second per megaparsec. This means that for each megaparsec, or about 32 million light-years, an object recedes from us at that speed. In contrast, when astronomers use supernovas and other local measurements, they find a value of around 73 kilometers per second per megaparsec. These contradictory figures have perplexed scientists and raised questions about our understanding of the cosmos. The importance of this Hubble tension goes beyond mere numbers. It calls into question our fundamental understanding of the universe's dynamics. If the discrepancy persists, it could indicate unknown physics beyond our current models. This includes possibilities such as new types of dark energy, variations in dark matter properties, or even the need to revise our understanding of gravity itself. Each possible explanation opens interesting avenues of research as scientists design experiments and observations to test these theories. This tension represents a potential change in our understanding of cosmic evolution, as researchers delve into not only the speed of expansion, but also its implications for the final destiny of the universe. The Hubble tension reminds us in a convincing way that, although we have unraveled many mysteries, the universe still has secrets to discover. Each piece of data brings us one step closer to a more complete picture of the vast cosmos, and overcoming this challenge may reveal a richer and more nuanced understanding of the universe we inhabit. In the vast realm of cosmology, scientists have proposed several theories to explain the puzzling observation that our universe is expanding at an accelerated rate. One of these intriguing explanations comes from the so-called vacuum models. At first glance, the idea may seem counterintuitive, but it depends on understanding the universe's structure itself. Vacuum models propose that our universe is not uniformly filled with matter, but consists of large empty regions known as voids interspersed with denser areas filled with galaxies and clusters. In these models, the expansion of space is perceived differently depending on location. Observations indicate that distant galaxies appear to recede from us at ever-increasing speeds. However, vacuum models suggest this is not necessarily due to a mysterious force often called dark energy, but rather to the geometry of cosmic structures. When we consider a region full of galaxies, they exert a gravitational attraction on each other, slowing expansion in their environment. In contrast, voids, which contain less matter, allow a more accelerated effect on the expansion rate. When we observe distant galaxies, we may be perceiving a predominantly empty region, thus interpreting this movement as an accelerated expansion, even when it is the result of the cosmic landscape. This perspective encourages us to reevaluate our fundamental assumptions about the universe's composition. Vacuum models may not completely eliminate the need for dark energy, but they challenge us to closely investigate how matter's grouping affects our understanding of cosmic expansion in a universe as vast and intricate as ours. Addressing these questions with these alternative models broadens our understanding and sustains the search for knowledge. Baryon acoustic oscillations are an intriguing piece of the cosmic puzzle closely linked to the early universe's development just after the Big Bang. The universe was filled with a hot, dense soup of particles, including protons, neutrons, and electrons. As it expanded and cooled, these particles began to clump together, forming the first atoms. However, before this grouping stabilized, sound waves traveled through the hot plasma, creating waves. When the universe cooled enough for atoms to form, these waves ceased, leaving specific patterns in the distribution of galaxies. These patterns act as a cosmic ruler. When we observe the distribution of galaxies today, the positions of those waves created by the baryon acoustic oscillations can be measured, giving us a standard length scale, since these acoustic waves created a characteristic distance of about 500 million light-years between clusters of galaxies. Scientists can use this scale to determine how the universe expands over time, basically comparing the current distance between galaxies and that standard ruler. We can deduce how fast the universe stretches as it expands. The light from distant galaxies stretches in a phenomenon known as redshift. By examining redshift data along with distances measured through baryon acoustic oscillations, researchers can construct a detailed picture of cosmic expansion. This method has proven to be a crucial tool that contributes to our understanding of phenomena, such as dark energy, which appears to be causing this expansion's acceleration. This method has proven a crucial tool that contributes to our understanding of phenomena, such as dark energy, which seems to be causing the acceleration of this expansion. The acoustic oscillations of baryons provide both a snapshot of the early universe and a way to follow its evolution over billions of years. They allow scientists to weave together the threads of cosmic history, linking the faint whispers of the early universe with the vast expanding cosmos we see today. This interaction between the ancient echoes of sound and the modern fabric of galaxies makes baryon acoustic oscillations a remarkable topic in the study of cosmology. The history of the universe is one of continuous change, and the recent discovery of its accelerated expansion introduces new mysteries about its final destiny. For a long time, astronomers believed that gravity, the force exerted by all masses, would slow this expansion down. However, over time observations, particularly of distant supernovas, revealed that, instead of slowing, the universe is expanding at an accelerated rate. This phenomenon is attributed to a mysterious force known as dark energy, which appears to constitute around 70% of the total energy of the universe. As galaxies move further away from each other due to this expansion, the implications for the cosmos become profound if the current trend continues. Clusters of galaxies could end up isolated as islands in a vast ocean, giving rise to a universe in which distant worlds move beyond the limits of our observable horizon. The final destiny of the universe could unfold in several fascinating scenarios. One possibility is the Great Freeze, in which continuous expansion gives rise to a cold, dark, and lonely universe, full of stars and galaxies that fade as energy dissipates over trillions of years. Galaxies could move beyond our gaze, and the night sky could become hauntingly empty, leaving only the faintest glimmers of light from the most distant remnants of existence. Another theoretical outcome could be the Great Rip. In this scenario, the force of dark energy could increase over time, tearing apart galaxies, stars, planets, and eventually even atomic structures. This would create a cosmic end in which the fabric of the universe itself falls apart. While the details of these scenarios remain speculative, they highlight how dark energy and accelerated expansion could lay the foundation for a universe that evolves towards isolation or dissolution. By observing the cosmos, we glimpse a great story in which the very nature of reality is constantly changing before our eyes. The Pioneer anomaly refers to an unexpected deviation in the trajectories of the Pioneer spacecraft, specifically Pioneer 10 and Pioneer 11, as they traveled through the confines of our solar system. Launched in the early 70s, these spacecraft aimed to explore the outer planets. However, as they moved away from the Sun, they showed a slight but measurable deceleration that did not align with predictions based on known gravitational influences. This anomaly puzzled scientists for years, as they initially considered various explanations ranging from solar radiation pressure to the gravitational attraction of unknown celestial bodies. However, none sufficiently explained the observed effects. The deviations seemed constant and continued as the spacecraft moved away from the Sun, causing intrigue and speculation in the scientific community. Eventually, researchers proposed more plausible explanations that focused on thermal effects. The spacecraft were equipped with various instruments that generated heat, and as they moved through space, this heat was radiated unevenly. This uneven radiation caused small thrusts that could explain the trajectories of the spacecraft. Although this thermal model explains the anomaly, it does not rule out the possibility that other factors contribute to the phenomenon. Although the Pioneer anomaly has been largely resolved thanks to this thermal explanation, it remains a stimulating topic in cosmology and serves as a reminder of the complexities involved in space exploration, inviting scientists to reevaluate our understanding of the gravitational forces acting on spacecraft traveling through the cosmos. The quest to fully understand the Pioneer anomaly has not only expanded our knowledge, but has also inspired deeper investigation into the mysteries of the universe. The cosmic microwave background radiation, often referred to as CMB, is a remarkable remnant of the early universe. It is the afterglow of the Big Bang that saturates the cosmos with an almost uniform temperature of approximately 27 degrees above absolute zero. However, although this radiation is remarkably uniform, scientists have discovered several inexplicable characteristics that challenge our understanding of the universe's first moments. One of the most notable is the anomaly of temperature fluctuations within the CMB. These small temperature variations, of approximately 1 part in 100,000, point to density differences in the early universe that ultimately led to the formation of galaxies. However, there are specific areas in the sky where the patterns of these fluctuations do not align with the standard cosmological model. Some scientists have proposed that these characteristics could point to new physics beyond the current understanding of cosmology. Another puzzling aspect is the so-called cold spot in the CMB, an area that appears unusually cold compared to its surroundings. This cold spot has intrigued researchers for years, sparking debates about its origin. Some theories suggest that it could be caused by a large supervoid, a huge empty region of space that would distort the CMB radiation. However, others speculate that these peculiarities in the cosmic background could indicate a broader panorama that perhaps involves interactions of our universe with others in a multiverse scenario. In addition, there are also anomalies in the polarization of the CMB. The polarization pattern can provide information about the early universe, particularly with regard to gravitational waves. However, the observed patterns often defy expectations, leading some scientists to question whether there might be alterations to the standard model that could explain these discrepancies. As we delve deeper into the mysteries of the cosmic microwave background, it becomes clear that each unanswered question opens up new realms of cosmic wonder and exploration, expanding the limits of our understanding of the universe's origin. Galactic rotation curves are graphs that show how the speed of stars and gas within a galaxy changes with distance from the galaxy's center. When astronomers first measured these curves in the mid-20th century, they encountered a surprising result. The outer regions of galaxies moved much faster than expected according to the laws of gravity defined by Isaac Newton. We would expect the speed of these stars to decrease significantly with distance from the galactic center. Instead, the speeds remained relatively constant, indicating a problem in our understanding of gravity on a galactic scale. This observation challenged existing theories about gravity and led to the proposal of dark matter. Dark matter is an invisible form of matter that does not emit, absorb, or reflect light. It is believed to constitute about 27% of the total mass of the universe, but cannot be observed directly. The idea is that dark matter exists in a vast halo surrounding galaxies and exerts a gravitational influence, keeping the stars in those outer regions moving at such high speeds. This revelation transformed our understanding of the universe, suggesting that what we see is only a fraction of what truly exists. However, The search for answers did not stop there. Some scientists began to question whether the laws of gravity themselves might need adjustment instead of relying solely on dark matter. Alternative theories, such as modified Newtonian dynamics or the Mond theory, suggest that gravity behaves differently at large scales and with low accelerations, typical of galactic systems. These adjustments aim to explain the observed rotation curves without resorting to dark matter, but introduce new complexities in our understanding of fundamental physics. In conclusion, galactic rotation curves confront us with mysteries that expand our understanding of both gravity and the universe itself. Whether we attribute the phenomenon to dark matter or to a revision of gravitational theory, the implications are significant. This ongoing research into the structure of the cosmos invites us to continue exploring the unknown, shedding light on the very essence of our universe and the forces governing it. Each new discovery shapes our perspective and reminds us how much we still have to learn. The flyby anomaly is a fascinating phenomenon that has puzzled scientists since its discovery in the late 20th century. It refers to an unexpected increase in speed observed by spacecraft during gravitational assists or flybys of planets. When spacecraft such as Galileo and Cassini pass near Earth or other celestial bodies, they gained more speed than the laws of physics as we understand them had predicted. This unexpected boost caught attention and triggered a series of theories and investigations. The key to the anomaly lies in its implications for our understanding of gravity, momentum, and the broader laws that govern motion in space. The boost seems to occur without any apparent external force being applied, which contradicts our understanding of physics. Scientists have explored various explanations for this phenomenon, ranging from effects related to the spacecraft hardware to more exotic theories involving modifications of fundamental physics. In examining potential explanations, researchers have considered everything from small thermal effects, such as uneven heating of the spacecraft surfaces, to the possibility of unknown forces acting on it. Despite numerous investigations, the definitive cause remains unknown. This uncertainty motivates a deeper exploration of the workings of our universe and has led to efforts in various scientific disciplines to analyze and validate findings. The flyby anomaly serves as a reminder of the complexity and mystery of space exploration. Each new discovery challenges our established understanding and illuminates the gaps that still exist in our knowledge of physics. As scientists continue to investigate this anomaly, they're not only approaching an understanding of this specific phenomenon, but are also contributing to a broader understanding of the forces at work in our universe. Ultra-high-energy cosmic rays are some of the most energetic particles observed in the universe. They are charged particles, mainly protons or atomic nuclei, that travel through space at speeds close to that of light. What makes them so extraordinary is their incredible level of energy, which can reach more than a quintillion electron volts. To put it in perspective, that is 1 billion times more energetic than the particles produced in the most powerful man-made accelerators. The origins of these cosmic rays remain largely a mystery, although we understand that they must come from extreme astrophysical events such as supernova explosions or active galactic nuclei. Exactly how they obtain such immense energy remains an unanswered question. The journey these particles undertake is also fraught with challenges, as they lose energy traversing the vast expanses of space by colliding with cosmic microwave background radiation, further complicating the tracking of their sources. Scientists have made substantial progress in detecting these cosmic rays using huge observatories that can measure their properties when they interact with Earth's atmosphere. However, despite our technological advances, it has only been possible to trace the origin of a small fraction of these high-energy particles to specific cosmic phenomena. This lack of global understanding increases their intrigue, as each detected cosmic ray can reveal a fragment of a much broader cosmic story. Ultimately, ultra-high-energy cosmic rays challenge our current model of astrophysics and particle physics. Their study not only expands the limits of our knowledge about the universe, but also invites us to consider the fundamental forces and processes at work in deep space. Unraveling these mysteries could pave the way for a new understanding of the cosmos itself. The cosmological principle is a fundamental concept in modern cosmology that states that the universe is homogeneous and isotropic when viewed on large scales. This suggests that, statistically speaking, the universe looks the same regardless of where it is observed from. However, large quasar groups pose an intriguing challenge to this principle. These enormous clusters of quasars, which are the luminous centers of distant galaxies, can create significant variations in density on large scales. Quasars themselves are amazing. They are powered by supermassive black holes and emit enormous amounts of energy, often eclipsing their galaxies. When astronomers observe large groups of quasars, they find that these structures can form dense regions in the universe. The presence of these clusters raises questions about the underlying uniformity of the cosmos, especially since they appear to exist where one would expect the universe to be more uniformly distributed. Furthermore, these dense groups of quasars can span great distances, sometimes reaching hundreds of millions of light years across, challenging our understanding of how matter and energy are distributed in the universe. If the universe were truly homogeneous, we would not expect to see such pronounced concentrations of quasars. Instead, these formations could imply that there are cosmic structures and phenomena that cause variations in how matter exists on a large scale. The discovery of large groups of quasars invites scientists to re-examine the assumptions of the cosmological principle and raises critical questions about the evolution of structures in the universe, suggesting that perhaps the cosmos has anisotropic regions or areas that differ significantly in their composition and distribution. This ongoing research fuels our understanding of the universe and reminds us that even well-established scientific principles are subject to refinement as we gain new knowledge. The Great Attractor is a gravitational anomaly located in intergalactic space, approximately 200 million light-years from Earth toward the constellation Centaurus. This immense region of gravitational attraction plays an important role in the movement of galaxies within our local supercluster, known as the Lanaka supercluster. The Great Attractor is not a single object, but an enormous concentration of matter possibly formed by several galaxy clusters hidden by the dense clouds of dust and gas between us and this mysterious region. One of the main challenges in studying the Great Attractor is the presence of cosmic dust, similar to haze that can obscure our vision of distant landscapes. This dust blocks much of the light from objects located in that direction, so conventional optical telescopes have difficulties providing clear images of the area. Astronomers have had to resort to radio and infrared observations to obtain information, but these types of observations require advanced technology and techniques to interpret the data precisely. In addition, the location of the Great Attractor makes its clear observation from Earth difficult, since it is located in a part of the sky that contains a large amount of other cosmic structures that cause confusion and complicate measurements of distances and speeds of surrounding galaxies. The complex interactions between these galaxies make it difficult to determine the properties of the Great Attractor and the scope of its influence with precision. Despite these obstacles, researchers continue to unravel the secrets of the Great Attractor. They are employing innovative methods, such as mapping the movement of galaxies, to develop a clearer picture of this intriguing region. By gathering data from various astronomical disciplines, scientists hope to better understand the Great Attractor and its role in the great tapestry of the universe, a search that illustrates the eternal wonder of cosmic discovery in the vast expanse of the universe. The massive vacuum voids, large regions of space with far fewer galaxies in their surroundings, are intriguing phenomena that challenge our understanding of the formation of cosmic structure. These voids can extend over hundreds of millions of light years, creating a disconcerting contrast with the dense clusters of galaxies that we usually observe. Their existence raises important questions about how matter is distributed in the universe and invites us to reconsider the models we use to explain cosmic evolution. Traditionally, cosmological models have been based on the idea that matter clumps together under the influence of gravity, forming structures such as galaxies and clusters over time. The discovery of enormous empty voids suggests that there is more complexity in this panorama than was thought. Researchers have begun to carefully study how these voids remain stable and why they persist without collapsing into denser areas, which challenges the predictions of conventional theories. In addition, the empty voids can affect our understanding of dark energy and dark matter, elusive components that are believed to play an important role in the expansion and structure of the universe. If the voids can maintain formations on such a large scale without the gravitational attraction and the expected interactions, this raises questions about the underlying physics that governs these forces, which leads scientists to explore the relationship between the voids and the large-scale architecture of the cosmos, potentially revealing information about the nature of dark energy. As ongoing observations and simulations continue to shed light on these voids, cosmologists are driven to refine existing theories and develop new models. The mystery of the enormous empty voids not only deepens our understanding of cosmic structures, but also awakens curiosity about the forces that shape our universe as a whole. Each discovery leads to more questions, which ensures that the exploration of these vast, empty spaces remains a vibrant area of scientific research. The cosmic microwave background, or CMB, is the afterglow of the Big Bang that fills the universe with a weak and uniform radiation, providing a snapshot of our early cosmos. Within this background, scientists have observed an intriguing feature known as the CMB cold spot. This region of the sky, approximately 100 million light-years in diameter, is characterized by a lower temperature than the surrounding areas of the CMB. Its importance lies in what it could imply about the evolution and composition of the universe. A prevailing theory suggests that the cold spot could be linked to a large-scale cosmic structure, such as a supervoid. A supervoid is an enormous region of space that contains far fewer galaxies than average, which could affect the way cosmological signals, such as the CMB, are perceived. This means that, as microwaves travel through these enormous voids, they could lose energy, which would lead to the observed temperature drop. If this is true, the cold spot could reveal important information about the distribution of matter and energy in the universe, helping to refine our models of cosmic evolution. However, some scientists propose a more exotic explanation. The cold spot could indicate the existence of other universes or multiverses. According to some interpretations of quantum physics and the theory of inflation, our universe could be just a bubble in a much larger cosmic foam of multiple universes. If the cold spot is the remnant of a collision between our universe and another, it could point to phenomena that challenge our fundamental understanding of reality. The importance of the CMB cold spot is profound. It not only offers possible clues about the structure and evolution of our universe, but also invites us to reflect on the very nature of existence. As cosmologists continue to study this puzzling feature, it acts as a portal to deeper questions about the cosmos and our place in it. Galaxies are not isolated islands in the vast expanse of the universe, but are part of a large cosmic network composed of enormous structures known as galaxy filaments. These filaments can extend over hundreds of millions of light-years, intertwining clusters of galaxies and defining the large-scale structure of the universe. Interestingly, these immense formations challenge our conventional understanding of physical limits. Theoretical models of cosmic structures originally suggested that there would be a maximum size for these filaments based on the gravitational forces that hold galaxies together. According to these models, the density and mass of gas and dark matter within a filament should reach an equilibrium that would limit its growth. However, astronomers have discovered filaments that significantly exceed these theoretical limits, which has led researchers to reconsider the mechanisms that drive their formation and evolution. One of the reasons why these galactic filaments can reach such amazing sizes has to do with the role of dark matter. Dark matter is a substance that does not emit light, but exerts gravitational influence. This mysterious component of the universe acts as a scaffold that allows matter to clump together and form larger structures, whereas the gravitational attraction of normal matter could limit growth based on density. The presence of dark matter facilitates a more extensive network. Another important factor is the ongoing cosmic evolution marked by mergers and interactions. As galaxies and clusters collide and merge, they can reshape the filaments that surround them. This process not only increases the effective reach of these structures, but also enhances their ability to accumulate surrounding gas and dark matter, creating a cosmic tapestry that extends far beyond what our theories initially anticipated. The understanding that galactic filaments can exceed theoretical limits not only deepens our understanding of the universe, but also highlights the mysteries still to be unraveled in cosmology. Tabby star, also known as KIC 846-2852, has captivated astronomers and amateur stargazers for its peculiar behavior. Observations have revealed that this star presents drastic and irregular fluctuations in its brightness, something different from any typical star. While most stars dim and brighten following predictable patterns, Tabby star's light curve presents drops that can be as high as 22%, baffling scientists interested in understanding the underlying causes. The main theories about these unusual light drops aim to explain what could be obstructing the intense light from the star. A popular hypothesis suggests that the fluctuations could be due to a swarm of comets surrounding the star, since when orbiting, the dust and gas of these comets could create a significant reduction in brightness when passing in front of it. However, the magnitude and unpredictable nature of these falls make definitively determining this scenario difficult. Another intriguing possibility calls attention to and awakens the imagination: the idea that an alien megastructure could be responsible for the eccentric behavior of Tabby's star. This hypothesis, although more speculative, suggests that a vast solar engineering project carried out by intelligent beings could be blocking the light of the star, although there is no direct evidence pointing to extraterrestrial origins. The mere idea has aroused considerable interest and debate within the scientific community and beyond it. Recent studies continue to provide information by examining the star's light fluctuations with advanced technology and new observations. These ongoing investigations aim to reveal the true reason behind the Tabby star's enigmatic pattern. With new discoveries on the horizon, the mystery could soon be solved, but for now the star remains an intriguing enigma that awakens wonder and curiosity in cosmic exploration. Hypervelocity stars are a fascinating cosmic phenomenon that attracts the attention of astronomers everywhere. These stars fly through space at amazing speeds, often exceeding 1 million miles per hour, challenging our understanding of stellar dynamics. Scientists have proposed several theories to explain how these high-speed travelers arose originally. A prominent explanation involves interactions with supermassive black holes at the center of most galaxies, including our own Milky Way. In these monstrous black holes, when a binary star system formed by two stars orbiting each other approaches a black hole, the intense gravitational forces can lead to a dramatic result. One star can be captured by the black hole, while the other is expelled at an immense speed, becoming what we know as a hypervelocity star. Another scenario suggests that hypervelocity stars can form in dense stellar environments, like globular clusters. In these crowded regions, stars can collide or closely interact, transferring momentum and energy between each other. When a star gains enough momentum from these interactions, it can escape the cluster's gravitational attraction and soar into the immensity of space at high speed. In addition, the study of these stars offers information about the structure of galaxies and star formation dynamics. By observing their trajectories and origins, scientists can better understand the history of the galaxies where they reside. The existence of hypervelocity stars is not only a curiosity, but they serve as vital clues that illuminate the complex gravitational dance within the universe. Through continuous observation, we discover the secrets of these cosmic wanderers, improving our understanding of the celestial mechanics at play here. Blue straggler stars are truly fascinating objects in the cosmos, known for their striking beauty and particularly unusual characteristics within globular clusters. These stars appear younger and hotter than their neighbors, which raises an intriguing question: how did they form? Several theories attempt to explain the origins of blue straggler stars, revealing the dynamic and sometimes violent nature of star clusters overall. A leading theory suggests that blue straggler stars result from stellar collisions in dense environments, such as globular clusters. Stars can be very close to each other, creating opportunities for interactions between them. When two stars collide, the combined material can form a single, more massive star overall. This star would be bluer and hotter, giving it the appearance of being younger than its older companions nearby. This process shows the chaotic dance of celestial bodies as they orbit their common center of gravity together. Another intriguing possibility involves the fusion of binary star systems together. Many stars exist in pairs that orbit each other in the dense environment of a globular cluster here. These binaries can interact with other stars. If a star in the binary evolves into a red giant, it can transfer material to its companion star directly. This process can lead to the companion gaining mass rapidly, changing its temperature and luminosity as a result overall. The receiving star can become a blue straggler star that appears to defy the expected life cycle of stars within the cluster. An alternative theory addresses the effects of mass transfer in binaries. In this scenario, a star in a binary system can extract material from its companion, effectively replenishing itself now. The increase in mass can push the star to evolve faster and emit light in the blue range of the spectrum, while its companion star, now stripped of some of its mass, becomes an aging star, increasing contrast between the two stars. Each of these fascinating theories contributes to our understanding of how recalcitrant blue stars challenge their environment in both age and life cycle, reinforcing the idea that the universe is full of surprises still. Magnetars are among the most fascinating objects in the universe, known for their incredibly powerful magnetic fields, which can reach levels 1,000 times stronger than those of a typical neutron star overall. To understand how these incredible fields are generated, we first have to consider the life cycle of a massive star itself. When such a star reaches the end of its life, it undergoes a supernova explosion that leaves behind a dense core now. If this core is massive enough, it can collapse and become a neutron star eventually. During this collapse, the star's rotation accelerates dramatically, similar to how a figure skater spins faster by bringing their arms together now. This increase in rotation, combined with the conservation of magnetic flux, causes the magnetic fields present in the star to be greatly amplified now. In the case of magnetars, this amplification reaches extreme levels. The processes that take place here are mainly driven by the intricate interaction of stellar dynamics and the physics of densely packed neutrons, which further distorts and enhances these magnetic fields greatly. Once a magnetar forms, its magnetic field continues to evolve and, at times, can become unstable too. The dynamics within this neutron star cause changes and rearrangements that can lead to even more powerful magnetic structures overall. One of the components of this is known as the Hall effect, in which the interaction of charged particles with a magnetic field can create complex magnetic configurations here. These configurations can lead to the generation of highly localized areas of intense magnetic energy on the magnetar's surface. As a result, magnetars not only possess extreme magnetic fields, but also exhibit fascinating phenomena, such as bursts of X-rays and gamma rays too. These bursts are generated when the magnetic field becomes so intense that it disrupts the surrounding environment completely. The extreme magnetic fields of magnetars are the product of stellar evolution, rotational dynamics, and the unique physics that occurs under extreme conditions, all united in a spectacular cosmic demonstration now. Each of these aspects contributes to our greater understanding of the universe and the incredible forces that act within it. Inside of variable stars like Betelgeuse are fascinating celestial objects that change their brightness over time due to a variety of reasons. Betelgeuse, located in the constellation of Orion, is a red supergiant star nearing the end of its life. Its dimming is particularly interesting because it can be influenced by intrinsic and extrinsic factors. One of the intrinsic causes of the dimming of Betelgeuse is the pulsation of the star itself as a red supergiant. It undergoes changes in size and temperature that can cause notable fluctuations in its brightness. These pulsations occur over periods ranging from a few hundred days to several years. During its expansion phase, the outer layer cools and expands, causing the star to dim. Conversely, when it contracts and heats up, it appears brighter. This natural cycle contributes to the overall variability of its brightness. Extrinsic factors also play a crucial role in the dimming of Betelgeuse. For example, the presence of dust clouds can obstruct the light that reaches us. These dust clouds can form when material from the star's outer layers is expelled into space, creating a veil that can periodically block our view of it. This interaction between the star and its environment adds an element of unpredictability to its brightness, making it difficult to determine exactly when the darkening will occur. In recent years, Betelgeuse has aroused great interest by presenting an unusual and spectacular dimming event, which has led many to speculate about its potential supernova state. Although the star will eventually explode in an impressive spectacle, this is not expected to occur until about 100,000 years from now. For now, Betelgeuse continues to captivate astronomers and enthusiasts, reminding us of the dynamic nature of the cosmos. Ultrametallic stars are a fascinating area of study in astrophysics, captivating scientists due to their rarity and importance in the cosmic timeline. These stars are characterized by having incredibly low concentrations of elements heavier than helium, which we often refer to as metals in astronomical terms. Their existence provides vital clues about the early universe, particularly about the formation of the first stars and the chemical evolution of galaxies. To understand the origin of these stars, scientists look back to a time shortly after the Big Bang. Initially, the universe was composed only of the lightest elements: hydrogen, helium, and a trace of lithium. The first stars, known as population 3 stars, formed from these primordial materials. They were massive and short-lived, generating the first heavier elements through nuclear fusion in their cores. When these stars ended their life cycles in supernova explosions, they scattered the newly formed metals into the surrounding space, enriching the interstellar medium. As new stars formed from this enriched material, they became what we classify as population 2 stars. However, in certain regions of the universe that did not experience much star formation or chemical enrichment, ultrametal-poor stars emerged. Scientists find these stars predominantly in the halo of our Milky Way and in dwarf galaxies. Their low metallicity indicates that they are some of the oldest stars in the universe, providing a direct window into the conditions of the early cosmos. The study of ultrametal-poor stars not only helps us trace the history of the formation of the elements in the universe, but also provides information about the nature of dark matter and how galaxies evolve over time. Each discovery deepens our understanding of our cosmic origins and the fundamental processes that have shaped the universe we observe. Today, the formation of supermassive stars, those titanic celestial bodies exceeding 100 times the mass of our Sun, has intrigued astronomers for decades. A prevailing theory suggests that these stars arise from the fusion of smaller stars in dense clusters. In the chaotic environment of these clusters, gravitational interactions can cause stars to collide and combine, giving rise to a much larger star. This process, which occurs over millions of years, implies that supermassive stars could form in relatively short time compared to the vast cosmic timescales generally associated with star formation. Another fascinating hypothesis revolves around the rapid accretion of gas in the early universe, particularly during its turbulent periods full of gas and dust. As these regions collapse under their own gravity, regions of space could become incredibly dense. The influx of surrounding gas can fuel the growth of an expanding star. This accretion process allows the star to rapidly accumulate immense amounts of material, potentially leading to the formation of supermassive stars. There is also a theory focused on the role of dark matter in facilitating the birth of these giants. Dark matter, the invisible substance that makes up a significant part of the mass of the universe, can influence the gravitational forces within galaxies. This gravitational backdrop can lead to the formation of massive gas clouds that, under the right conditions, could collapse directly into supermassive stars. This creates a scenario in which dark matter helps open paths for stars to grow to unprecedented sizes. Ultimately, the formation of supermassive stars appears to be a complex interaction of various processes, whether through stellar mergers, rapid gas accumulation, or the influence of dark matter. Each theory contributes a piece to the puzzle as we continue to study the universe. Astronomers hope to unravel more about these giant stars and their role in cosmic evolution, further expanding our understanding of the great tapestry of the universe. Some stars seem to defy our understanding of time by appearing older than the universe itself, an enigma that has fascinated astronomers for years. The universe is estimated to be about 148 billion years old, according to observations of the cosmic microwave background. Cosmic background and the expansion rate of the universe. However, when astronomers look deep into space, they sometimes discover stars with ages suggesting they formed only a few hundred million years after the Big Bang. This contradiction raises important questions about our understanding of cosmic evolution. One of the key reasons behind this apparent age discrepancy lies in the nature of our observations. The light we see from distant stars takes a long time to travel through space to reach us. For example, if we observe a star that is 13,000 million light-years away, we are actually seeing the light emitted when the star was much younger, just after it formed. This means that the star could appear older than the universe if we misinterpret the timeline of its existence based on its distance from us. Another factor to consider is the stellar population from which these stars come. Some of these ancient stars are part of a group known as population 2 stars. These stars formed in the early universe and are mainly found in globular clusters and are composed of older elements that formed before the cosmos had the opportunity to produce heavier elements through processes such as supernova explosions. This means that they typically have a low metallicity, which indicates that they are among the oldest stars, since they depended on the first generation of hydrogen and helium in the universe. To reconcile the age of these stars with the age of the universe, astronomers continually refine their models of stellar and galactic formation. While these discoveries may initially challenge our understanding, they provide an exciting vision of the early cosmos and the life cycles of stars. Each new finding invites us to reconsider our models of the universe and enriches our understanding of its history. Ultimately, each star continues to tell a story that reveals a fascinating chapter of the immense narrative of the cosmos. Cepheid variable stars are fascinating celestial objects known for their rhythmic variations in brightness. These stars are a type of pulsating variable star, which means they expand and contract in a regular cycle. The underlying cause of these pulsations lies in the balance between the star's gravity, which pulls inward, and the outward pressure of the heat generated in its core during nuclear fusion. As a star runs out of its hydrogen fuel in the core, it begins to contract under gravity. This contraction causes the temperature and pressure in the core to increase until, when the core becomes hot enough, the fusion of hydrogen ignites again, causing a surge of energy that heats the outer layers of the star. This energy creates an outward pressure that forces the star to expand. During this expansion, the brightness of the star increases dramatically, often becoming much more luminous than in its contracted state. However, this process is not permanent, since as the outer layers expand, the gravitational attraction begins to strengthen again, which leads to a decrease in temperature and pressure in the core. This cycle continues, causing the star to contract and brighten, then expand and dim in a beautiful, predictable rhythm. The pulsation period varies between Cepheids, and the duration of the cycle is related to its intrinsic brightness, which makes them valuable for measuring cosmic distances. Astronomers have used these pulsations as a cosmic rule that allows them to calculate distances to distant galaxies. The correlation between a Cepheid's brightness and its pulsation period provides us with a powerful tool to understand the scale of the universe. With each pulsation, These stars not only captivate our imagination, but also reveal the immensity of space and our place within it. Scientists have always been captivated by the diversity of stars observed throughout the universe. Among these celestial wonders are stars with chemical compositions that seem contrary to our expectations. For most stars, the elemental composition is mainly hydrogen and helium, the building blocks of the universe. However, there are atypical stars with unique chemical signatures that raise intriguing questions about their origins. One explanation for these unusual chemical compositions lies in the life cycles of the stars themselves. As stars evolve, they go through nuclear fusion processes that convert lighter elements into heavier ones. Massive stars, for example, can produce elements such as carbon, nitrogen, and oxygen, which are then released into space when they explode as supernovas. This enrichment of the interstellar medium can lead to the formation of new stars with variable elemental compositions that reflect the materials from which they condense. Another fascinating aspect is the idea of stellar mergers. Sometimes, two stars merge, giving rise to a new star that may possess a complex amalgam of chemical elements from both progenitor stars. This phenomenon not only alters the internal composition of the star, but can also influence its brightness and its lifespan. Astronomers have detected these events through light variations and chemical analysis, which helps them unravel the secrets of stellar formation and evolution. In addition, the environments where these stars form play a crucial role in their chemical composition. Stars born in regions rich in heavier elements, such as those found in clusters or near supernova remnants, may inherit different chemical traits compared to stars born in primordial gas clouds. This diversity in chemical composition enriches our understanding of stellar evolution and highlights how the universe forges its elements through an intricate network of processes over billions of years. Each star tells a unique cosmic story of creation, transformation, and the continuous journey of matter in the universe. The Fermi bubbles are two enormous balloon-shaped structures that extend above and below the center of our galaxy. The Milky Way, discovered in 2010 through observations made by the Fermi Gamma Ray Space Telescope. These gigantic bubbles extend about 50,000 light-years in height. What makes them particularly intriguing is their unique shape and the mystery surrounding their origin. Scientists believe these bubbles were formed by events such as star formation, supernova explosions, or powerful jets emitted from the supermassive black hole at the center of the galaxy. The energy from these processes can push gas and cosmic rays outward into space, creating the extensive bright regions we see today. The bubbles mainly emit gamma rays, which means they are incredibly energetic and represent some of the most violent and dynamic activities that take place in our galaxy. Another fascinating aspect of the Fermi bubbles is their relationship with the overall environment of the Milky Way. They may not be just random characteristics, but indicators of past and present activities within our galaxy. For example, the bubbles are believed to be a sign of an active galactic nucleus, which occurs when material is rapidly consumed by the black hole, leading to the expulsion of high-energy particles. Understanding the Fermi bubbles not only sheds light on the history of our galaxy, but also offers clues about the processes that govern the universe itself. They are a testament to the dynamic and sometimes violent nature of cosmic evolution, reminding us that the heart of our galaxy remains an intriguing and active area of research. Ultra-diffuse galaxies are a fascinating class of cosmic structures that captivate astronomers for their peculiar properties, unlike typical galaxies, which tend to be dense and compact. Ultra-diffuse galaxies possess a surprisingly low surface brightness and vast regions of empty space between the stars that give them a ghostly appearance, even though they contain billions of stars. Researchers are studying several theories to explain how these enigmatic formations exist and thrive in the universe. One of the main hypotheses suggests that ultra-diffuse galaxies could have formed from the remains of larger galaxies that were stripped of their gas and stars through gravitational interactions over time. These interactions could lead to the dispersion of the material, creating a faint galaxy that lacks the bright clusters typically associated with standard galaxies. Another perspective proposes that these galaxies could form in environments where dark matter is more prevalent, allowing stars to spread over great distances without significant gravitational attraction that keeps them in a compact structure. Interestingly, the study of ultra-diffuse galaxies also sheds light on the role of dark matter. In many cases, these galaxies appear to possess a considerable amount of dark matter, even if their visible components seem scarce. This raises questions about the relationship between dark matter and the formation of galactic structures, highlighting a complex interaction that remains a key topic among scientists. Understanding these dynamics can reveal more about the fundamental nature of our universe as researchers continue to unravel the mysteries of ultra-diffuse galaxies. New discoveries related to their formation and evolution promise to improve our understanding of the cosmos. These faint and extensive entities are a testament to the diversity of galaxies and the ever-evolving landscape of astronomical research. Each revelation brings us closer to understanding not only these galaxies themselves, but the broader mechanisms that govern the universe around us. Quasars, the intensely luminous nuclei of distant galaxies, have long fascinated astronomers. One of their most puzzling characteristics is the unexpected alignment of their rotation axes. This phenomenon suggests that, despite being located billions of light years away, these quasars appear to share a common direction in their orientation. But what drives this alignment? At the heart of a quasar lies a supermassive black hole that can rotate like a spinning top. The black hole's rotation is influenced by the gas and dust that falls into it, creating an accretion disk that emits tremendous energy. Researchers believe that certain environmental factors in the early universe, such as gravitational interactions or the dynamics of large-scale structures, could exert a significant influence on the spin of these black holes when they merged or formed. Massive galaxies merged or formed. Gravitational forces could have aligned the spins of the black holes within them, giving rise to the observed alignment of the axes of rotation of the quasars. Another layer to this mystery involves the notion of cosmic filaments, which form the large-scale structure of the universe. These filaments are essentially the scaffolding of the cosmos, composed of dark matter and gas that connect galaxy clusters. The orientation of the quasars could be related to these filaments, since large-scale gravitational influences could align the rotating black holes with the flow of matter in these structures. In addition, studies suggest that these alignment patterns could be an echo of the primordial conditions after the Big Bang. The universe was once homogeneous and isotropic, but as it evolved, slight density fluctuations gave rise to regions of greater gravity. These conditions could have laid the foundation for the alignment we observe today in the rotation axes of quasars. As researchers continue to investigate the interaction of gravity, cosmic evolution, and the physics of black holes, it remains an exciting frontier for understanding the cosmos. The formation of galaxies is one of the most fascinating processes in the universe, and current theory suggests that dark matter plays a crucial role in this cosmic ballet. However, if we consider a scenario without dark matter, the narrative would be very different in a universe devoid of dark matter. The formation of galaxies would still be possible, but it would follow a slower and more chaotic process in the universe's early moments. Small density fluctuations set the stage for the grouping of normal matter, composed mainly of hydrogen and helium. These regions where gravity was a little stronger due to their density began to attract more matter over time as groups of gas formed, would have experienced a gravitational collapse that would have led to the formation of stars. The absence of dark matter would mean that these gas clouds and their star formations will be mainly influenced by the visible mass, which is much smaller than the total mass in a traditional galaxy formation scenario. As these first stars began to form, they would produce heavy elements through nuclear fusion, which would eventually be expelled back into space after their death. This process would enrich the surrounding gas and fuel the formation of new stars, creating a cycle of stellar birth and death. These stars would have diverse sizes and lifespans, and, without the stabilizing influence of dark matter, the The gravitational interactions between them and the surrounding gas would be crucial. Stars could have formed in smaller groups or associations rather than in large clusters, as the additional gravitational attraction of dark matter would normally help bind these structures together over time. These smaller groups could collide and merge, leading to the gradual creation of larger aggregate structures that we recognize today as galaxies. Although the resulting galaxies might resemble their dark matter counterparts in structure, they would likely be less stable and could change more drastically over the eons. Without dark matter, the evolution of galaxies would be more volatile, resulting in a universe dotted with diverse and perhaps more fragmented galactic structures. This thought experiment reminds us how crucial dark matter is in shaping the universe we see today, but also shows the resilience and adaptability of matter in the cosmos, capable of forming galaxies even in different circumstances. High-velocity clouds in the galactic halo are fascinating structures that tell us a lot about the dynamics of our galaxy. They are essentially gas clouds that move rapidly, often at speeds greater than the typical rotation speed of the Via Láctea. These clouds are mainly composed of hydrogen, the most abundant element in the universe, and scientists have established two main sources for these intriguing formations. One significant source is the so-called substrate of the galactic disk, as the stars in the galaxy, throughout their life cycles, produce stellar winds and supernovas. These explosive events can expel gas from the disk into the halo, giving rise to high-velocity clouds. This process aligns with the idea that galaxies are dynamic systems that continuously exchange matter between their various components. Another source comes from interactions with other galaxies when our Via Láctea encounters smaller companion galaxies, such as the melancholic clouds. Gas can be torn off and accelerated into the halo. This cosmic ballet of gravitational interactions and tidal forces often results in the formation of velocity, as the material is dragged and accelerated to high speeds. The study of these clouds helps astronomers understand the complex processes that drive the evolution of galaxies and provides information about the conditions of the intergalactic medium and the interactions within the cosmic network of structures. Essentially, high-velocity clouds serve as an interconnected thread that weaves the story of how galaxies like our Via Láctea are formed by both their internal dynamics and their cosmic relationships. The mysteries of star formation in galaxies continue to challenge our understanding of the universe. While traditional models suggest that there should be a decrease in star formation over time as gas reserves are depleted, some galaxies defy these expectations by maintaining surprisingly high rates of star formation. These galaxies, called starburst galaxies, can produce new stars at rates that are several times greater than those of our own Milky Way. A key factor in these galaxies is their abundant supply of cold gas. Cold gas is crucial because it is the raw material needed for star formation. In many of these starburst galaxies, enormous clouds of cold molecular gas predominate, providing the necessary ingredients for new stars to form. Observations at various wavelengths, such as radio and infrared, have revealed vast reserves of this cold gas, often triggered by cosmic events such as galaxy mergers or interactions with other galaxies that compress the gas clouds and trigger star formation. In addition, the environment plays an important role in dense groupings of galaxies, such as those found in clusters, as gravitational interactions can cause shocks and instabilities in the gas, which can further stimulate star formation. Active galactic nuclei, extremely bright and energetic centers found in some galaxies, can also influence star formation through feedback mechanisms that regulate the flow of gas, either encouraging or preventing the birth of new stars. This interaction between gas availability, environmental conditions, and dynamic processes keeps star formation running in ways that traditional models struggle to explain fully. As astronomers use more advanced telescopes and instruments to probe these galaxies, each discovery paints a more detailed picture of our universe, revealing not only the complexity of star formation, but also how much remains to be learned about the vast cosmos surrounding us. Polar ring galaxies are fascinating cosmic structures that allow us to understand the complex dynamics of galaxy interaction and formation. These galaxies are characterized by unusual shapes, often featuring a prominent ring of stars and gas orbiting the central galaxy at a sharp angle with respect to their disk. So, what causes these distinctive formations? The formation of polar ring galaxies is primarily the result of gravitational mergers and interactions between galaxies. At some point, a smaller galaxy passes near a larger one, and the gravitational attraction of the latter can tear material from the smaller one, accumulating it in an annular structure that orbits around it. This process is similar to a cosmic dance in which the forces at play allow for a beautiful, chaotic reorganization of matter and space. The orientation of the polar rings, which is often perpendicular to the main disk, can be explained by the dynamics of the interaction. The orbit of the smaller galaxy can enter at an inclined angle, leading to the formation of rings that lie in a different plane than the main galaxy's disk. This unique arrangement creates a visual spectacle that shows how diverse and complex the arrangements of galaxies can be. Interestingly, some galaxies with polar rings can evolve, allowing ring material to gradually transfer to the central galaxy. This process can lead to changes in the structure and appearance of both the central galaxy and the ring, altering their interactions and star formation. Understanding polar ring galaxies not only reveals the mechanism underlying their striking shapes, but also helps us understand the broader processes of cosmic evolution that shape our universe. Scientists have long been fascinated by the presence of galaxies that appear more developed than their estimated age suggests. Observing distant galaxies is like looking back, and many of these enigmatic structures show characteristics typical of much older galaxies. This contradiction raises questions about how galaxies evolve and develop over time. One of the main explanations revolves around the concept of rapid star formation in the early universe. Conditions were radically different, allowing gas and dust to quickly coalesce, triggering intense bursts of starbirth. These events could lead to galaxies forming stars at a frenetic rate, creating the impression of a more mature galaxy sooner than expected. In addition, this rapid formation could lead to the development of complex structures such as spiral arms or bulges that usually signify a mature galaxy. Another key player in this cosmic enigma is the role of mergers. Galaxies are not solitary entities. They often collide and merge. This process can accelerate star formation and lead to growth, giving the appearance of maturity. When two or more galaxies collide, they can produce an impressive array of new stars and rejuvenate existing ones, resembling a galaxy that has had more time to evolve than it actually has. These dynamic interactions can sculpt galaxies into shapes and structures that we often associate with older cosmic communities. Advanced observation technology has allowed scientists to look deeper into the cosmos, revealing these young galaxies and giving rise to new theories about galaxy formation, such as the theories of dark matter halos that play a crucial role in gravitational interactions, or the influence of cosmic rays and magnetic fields, which continue to provide information as researchers unravel this complex tapestry of cosmic history. The existence of mature-looking galaxies may simply reflect a more intricate timeline of a universe's development than previously understood. This ongoing exploration guarantees that our understanding of the universe's evolution remains vibrant and full of surprises. M82, often called the cigar galaxy due to its shape, presents an extraordinary phenomenon known as galactic wind. This wind is essentially a colossal emission of gas flowing from the galaxy into space. It creates a striking contrast with its generally calm and star-filled background. But how does such a remarkable feature form? The origin of this galactic wind involves intense star formation. M82 is experiencing a period of rapid star formation, meaning that numerous massive stars are being born in a relatively short period of time. These massive stars have relatively short lives, often only a few million years, and when they reach the end of their lives, they explode as supernovas, These colossal explosions release immense energy and shock waves that push material outward and drive the galactic wind. To top it off, the winds generated by these massive stars further contribute to the phenomenon. Stellar winds are streams of charged particles ejected from stars, and when many massive stars go through this simultaneously, the collective effect can be extraordinary. These winds join forces, creating a powerful stream of gas and dust that ultimately leads to the galactic wind that we observe in M82. This stream can move at remarkable speeds, sometimes reaching thousands of kilometers per second. The galactic wind not only carries gas and dust away, but also plays a crucial role in the galaxy's evolution. It can affect star formation rates and the recycling of materials, altering its structure and dynamics over time. The interaction between star formation and galactic winds makes M82 a fascinating laboratory to study the life cycle of galaxies in our universe. The ultraluminous infrared galaxies, or ULIRGs, are among the most surprising objects in the universe, capable of emitting more energy than our entire Milky Way galaxy. What distinguishes them is their amazing luminosity, which often exceeds 1 trillion times the brightness of the sun. The main source of this incredible energy resides in the intense activity that occurs inside these galaxies, especially at their centers. In the heart of a ULIRG, there often is a supermassive black hole that devours the surrounding gas and dust at an amazing rate. This process, known as accretion, produces immense amounts of energy as matter swirls toward the black hole, heats up, and emits radiation, much of which is in the infrared spectrum. This is mainly due to all the dust and gas present in the galaxy, which absorb the radiation and re-emit it in the form of infrared light. It is this combination of a feeding black hole and dense clouds of gas and dust that results in the luminous ULIRG. Another key factor in the high luminosity of these galaxies is the star formation that ULIRGs usually experience during a period of rapid star formation driven by interactions and collisions with other galaxies. When galaxies collide, their gas and dust are compressed, leading to conditions conducive to the birth of many new stars. The energy produced by these star formation regions also contributes significantly to the infrared luminosity of the galaxy. The newly born stars emit light that can be absorbed and re-emitted by the surrounding dust, creating a vibrant glow. Interestingly, many ULIRGs come from the early universe, indicating that these energetic processes were much more common in the cosmic past. As a result, the study of these galaxies not only helps us understand the current universe, but also provides a deep insight into the formation and evolution of galaxies throughout cosmic history. The extreme luminosity of the ULIRGs remains a source of fascination that reveals the incredible dynamics that unfold in the universe. Ultra-high-energy cosmic rays are among the most energetic particles in the universe, with energies exceeding 10 quintillion electron volts. Their origin has long intrigued scientists, arousing curiosity and research around the world. These cosmic rays are charged particles, mainly protons, that travel through great distances before reaching Earth. Their extreme energies suggest that they originate in some of the most violent and energetic processes in nature. One of the main hypotheses points to supernovas and the remains they leave when a massive star explodes at the end of its life, creating shock waves that can accelerate charged particles to incredible speeds. However, although supernovas play an important role in the production of cosmic rays, the most energetic particles probably come from even more powerful sources. These include active galactic nuclei, which are believed to harbor supermassive black holes. As matter swirls into these black holes, it heats up and emits jets of particles that can accelerate them to ultra-high energies. Another exciting possibility is gamma-ray bursts, brief but intense bursts of gamma radiation typical of some of the most energetic events in the universe. These explosions are believed to occur during the collapse of massive stars or the fusion of compact objects such as neutron stars. The conditions during these cataclysms could propel particles to the incredible energies associated with ultra-high-energy cosmic rays. Despite these theories that point to the exact sources of these cosmic rays, it remains an ongoing astronomical challenge. Current detection efforts focus on identifying the traces left by these energetic particles as they collide with the Earth's atmosphere. As researchers continue to explore the cosmos with advanced telescopes and observatories, they are getting closer to unraveling the mysteries behind the origins of the universe's most energetic messengers. Cosmic rays are incredibly energetic particles that originate outside the Earth's atmosphere. They consist mainly of protons and atomic nuclei, and when we talk about them, we are often surprised by their high energies, which can even exceed those created in artificial accelerators. So, how do these particles manage to accumulate so much energy in the immensity of space? One of the main mechanisms for the acceleration of cosmic rays is through supernova explosions. When a massive star reaches the end of its life, it can explode in a bright supernova, sending shock waves through space. As these shock waves travel, they can accelerate particles to tremendous speeds. Imagine these shock waves as powerful engines that launch protons and heavier nuclei into the cosmos at speeds close to that of light. This process is known as diffusive shock acceleration. Another important source of high-energy cosmic rays is found in the regions around black holes, particularly in active galactic nuclei. As matter spirals inward towards a black hole, it heats up and accelerates to extremely high speeds due to the intense gravitational forces. These turbulent environments can propel particles to energies much higher than we can achieve on Earth. It is fascinating to think that some of the most energetic cosmic rays could be produced near these enigmatic giants of our universe. Finally, the interactions between the cosmic rays themselves contribute to increasing their energy. When high-energy particles collide, they can create showers of secondary particles that inherit some of the original energy. This continuous process creates a cosmic ballet of accelerating particles. And in the end, the cosmic rays that we detect on Earth are the result of a variety of dynamic and powerful astrophysical events that occur throughout the universe. The next time you look at the night sky, remember that there are high-energy particles running through the cosmos with stories of incredible journeys that stretch across galaxies. The cosmic ray spectrum is a fascinating view of the behavior and origin of high-energy particles in our universe. Two notable characteristics of this spectrum are known as the knee and the ankle. These distinctive points reveal essential information about how cosmic rays travel through space and their interactions with our atmosphere. The knee appears at energies of around 10 million gigaelectronvolts. At this point, there is a notable drop in the number of cosmic rays detected. Scientists believe that this change is due to the depletion of protons produced in supernova remnants, meaning that as cosmic rays reach higher energies, fewer can originate from these sources. Essentially, the knee suggests a transition in cosmic ray sources as energy increases. Cosmic rays can come from more exotic systems, such as active galactic nuclei, or potentially even more powerful sources like gamma-ray bursts. Next, we find the ankle located at energies of around 1 billion giga-electronvolts. Here, an increase in the number of cosmic rays is observed, indicating a change in composition. This could indicate a mixture of sources where both protons and heavier nuclei contribute significantly to the observed cosmic rays. The ankle is essential to understanding how these particles propagate through space and interact with interstellar matter. In general, these characteristics not only illuminate the energy distribution of cosmic rays, but also pave the way for deeper investigations into the mechanisms that produce them. They shorten the distance between local astrophysical processes and the vast cosmic structures shaping our universe. The knee and the ankle can improve our understanding of cosmic ray acceleration and propagation, ultimately enriching our knowledge of the universe itself. Cosmic rays are high-energy particles that travel through space at speeds close to light. When they collide with molecules of the Earth's atmosphere, they can create secondary particles and ionize air molecules, which leads to intriguing interactions that can influence the weather, the climate, and one of the most notable effects of cosmic rays is their potential role in cloud formation, a process that has captivated scientists for decades. When cosmic rays collide with atmospheric gases, they help produce ions that can serve as nuclei around which water vapor condenses to form clouds. This process is known as ion-induced nucleation. Researchers have proposed that an increase in cosmic rays could lead to increased cloud formation, which could alter weather conditions by increasing cloud cover. Clouds play a crucial role in regulating Earth's temperature and can reflect sunlight back into space, cooling the planet. Conversely, they can also trap heat, which has a warming effect. Interestingly, the influence of cosmic rays on cloud formation is not uniform. Changes in cloud cover can affect regional climates differently. For example, an increase in low clouds can lead to cooler temperatures during the day, while a decrease in cloud cover can lead to more solar radiation reaching the Earth's surface, warming the planet. This interaction between cosmic rays, cloud formation, and climate is complex and influenced by various factors, including solar activity and the Earth's magnetic field. Studies have found correlations between cosmic ray levels, solar cycles, and climate variations over long periods. However, the scientific community continues to investigate these connections, and although the idea is compelling, it remains a piece of a much larger puzzle. The climate is affected by numerous interconnected factors: the oceans, the land, human activity, and much more, making it a rich field for ongoing research. As we deepen our understanding, the role of cosmic rays may reveal more about the intricate dance of the Earth's climate system. Cosmic ray anisotropy refers to the uneven distribution of cosmic rays in the sky. These high-energy particles, mainly protons, originate in various astrophysical sources, such as supernovas, black holes, and even the Sun. The importance of this anisotropy lies in the information it provides about our universe and the processes that shape it. By studying how cosmic rays travel through space and interact with magnetic fields, scientists obtain essential information about cosmic events and the structure of our galaxy. One of the crucial aspects of cosmic ray anisotropy is its connection to the sources of these energetic particles. By observing areas with a higher density of cosmic rays, researchers can identify regions rich in astrophysical phenomena. For example, if an area shows a significant number of cosmic rays coming from a specific direction, this may suggest that a powerful source, such as a supernova remnant or an active galactic nucleus, is accelerating these particles. This research enhances our understanding of cosmic processes and helps trace the origins of celestial energies. In addition, cosmic ray anisotropy serves as a probe for the interstellar medium, the matter that resides between stars. As cosmic rays travel through this medium, they interact with magnetic fields and other particles that can alter their trajectories. The analysis of the patterns of these particles provides valuable information about the composition and behavior of the interstellar medium. It is very similar to mapping a landscape through the movement of tiny travelers who reveal the hidden characteristics of our galactic neighborhood. Finally, cosmic ray anisotropy can also shed light on fundamental questions of physics, as it challenges existing theories about cosmic ray propagation and could provide clues about new physics beyond our current understanding. Whether investigating the forces that govern particle acceleration or probing the nature of dark matter, the study of cosmic ray anisotropy remains a vibrant field that continually contributes to our broader understanding of the mysteries of the universe. Cosmic rays are high-energy particles that travel through space at a speed close to that of light. Most of the cosmic rays that reach Earth are believed to originate from sources such as supernovas and active galactic nuclei. However, there is a fascinating phenomenon known as the Greason-Zatsepin-Kuzmin limit, or GZK limit, which suggests that cosmic rays above a certain energy threshold should not be able to travel great distances without losing energy due to interactions with cosmic microwave background radiation. This limit is based on well-established physics, which predicts that ultra-high energy cosmic rays should lose energy through collisions and decay as they traverse the universe. However, astronomers have detected cosmic rays that exceed this energy limit, which present a mystery. One proposed explanation is that these particles could come from sources much closer to Earth than previously thought. For example, astrophysical events, such as gamma-ray bursts or certain types of active galaxies, can produce extremely energetic particles that can reach us without breaking the GZK limit, since their trajectories to our planet are relatively short. Another intriguing possibility is that some of these ultra-high energy cosmic rays could be generated by exotic astrophysical phenomena, such as topological defects from phase transitions of the early universe or hypothetical sources that we are currently unaware of, which could radiate particles that escape the energy loss mechanisms predicted by the GZK limit, revealing the potential for new physics that we have not yet fully understood. In addition, the extremely rare events of ultra-high energy cosmic rays that reach us could be the result of interactions within their sources that produce energy in a way that is not yet discovered. Ongoing research into these cosmic rays undoubtedly keeps scientists on the edge of their seats, as each new finding could open the door to entirely new realms of astrophysical understanding and challenge our understanding of fundamental physics in the cosmos. Supernova remnants are some of the most energetic and fascinating objects in our universe. When a massive star reaches the end of its life, it explodes in a dramatic event known as a supernova. The force of this explosion creates a shock wave that travels through space, interacting with the surrounding interstellar medium. This interaction is crucial because it is within these remnants where cosmic rays, high-energy particles that travel through the galaxy, accelerate as the shock wave expands, compressing and heating the interstellar gas and creating conditions conducive to particle acceleration in this environment. Charged particles, like protons and electrons, can gain energy by bouncing between shock waves. This process, commonly known as diffusive shock acceleration, allows these particles to reach speeds near that of light, transforming them into cosmic rays. Interestingly, supernova remnants are believed to be a main source of cosmic rays that we detect on Earth. Studies have shown that the highest energy cosmic rays likely originate in very powerful supernova explosions. The immense energy released during these events not only contributes to the creation of the heavy elements needed to form stars and planets, but also injects energy into the cosmos in the form of these rapidly moving particles. Supernova remnants act as cosmic laboratories where the interaction of shock waves and interstellar gas leads to the acceleration of cosmic rays throughout their life cycles. These remains not only enrich the galaxy with essential materials, but also play a fundamental role in the behavior of high-energy particles throughout the universe, shaping our understanding of cosmic phenomena. Cosmic rays are high-energy particles that travel through space and consist mainly of protons along with a small percentage of heavier nuclei and electrons. These particles are believed to originate from various sources, such as supernovas and active galactic nuclei. As they traverse the vast expanses of space, cosmic rays encounter the interstellar medium, a thin gas composed primarily of hydrogen, helium, and trace amounts of heavier elements. As cosmic rays collide with particles in the interstellar medium, they can initiate a series of interactions that produce secondary particles and radiation. For example, when a cosmic ray proton encounters a hydrogen atom, it can trigger a reaction that creates pions and tryons, which in turn decay into other particles, including muons and neutrinos. These processes not only generate new particles, but also contribute to the production of gamma rays, which are high-energy electromagnetic waves. The interaction is significant for a couple of reasons. First, it enriches the interstellar medium with heavier elements and contributes to the cosmic background radiation. Second, these interactions can influence the dynamics within the galaxy, since the products of cosmic ray collisions can generate shock waves that affect the movement and behavior of the surrounding gas. In addition, some of these secondary particles can eventually become cosmic rays, perpetuating the cycle of energy and matter in space. Understanding how cosmic rays interact with the interstellar medium helps scientists unravel the underlying dynamics of our galaxy and provides information about cosmic phenomena including star formation, and illuminates the processes that fuel the evolution of our universe. Each collision is a small chapter in the great narrative of cosmic interactions, revealing the intricate tapestry of matter and energy that traverses the universe. Cosmic rays and gamma-ray bursts are two fascinating phenomena of our universe, both intricately connected with the high-energy processes that take place beyond our planet. Cosmic rays are incredibly energetic particles like protons and atomic nuclei that travel through space at a speed close to that of light. They are believed to come from various sources, such as supernovas, active galactic nuclei, and, interestingly, also from gamma-ray bursts. These cosmic events produce immense amounts of energy and can accelerate particles to speeds that create the cosmic rays that we detect on Earth. On the other hand, gamma-ray bursts are among the most energetic explosions in the universe. They can release more energy in a few seconds than the sun will emit throughout its entire life. These bursts occur when massive stars collapse to form black holes or when neutron stars collide. The immense energy and conditions during these events not only produce gamma rays, but can also accelerate particles that contribute to the cosmic ray population that we observe. Both phenomena arise from extreme cosmic events, but express their energy in different ways. A particularly captivating aspect of their connection lies in the mechanisms that produce these high-energy particles. When gamma-ray bursts occur, they emit intense jets of energy and material. These jets can interact with surrounding matter or radiation, leading to particle acceleration. Consequently, when cosmic rays reach our atmosphere, they may be remnants of these dramatic cosmic activities. Their study allows scientists to draw a clearer picture of the energetic universe, linking the particles we detect on Earth with the violent processes that take place light years away. In addition, researchers continue to explore how gamma-ray bursts contribute to the overall composition of cosmic rays in the universe, improving our understanding of cosmic evolution. The relationship between these phenomena reflects the complexity of the cosmos, and as we delve into its mysteries, we discover the underlying principles that govern the universe itself. This interaction not only expands our knowledge of astrophysics, but also makes us wonder about the incredible events that take place in the universe, fueling our curiosity about the cosmos in which we live. Cosmic rays are high-energy particles that travel through space at a speed close to that of light and come from two main sources within our galaxy and beyond. Cosmic rays that originate outside our galaxy often include high-energy protons and heavier atomic nuclei, including elements such as iron. These particles carry enormous amounts of energy, much greater than those produced in our Milky Way. On the other hand, cosmic rays produced within the Milky Way usually have less energy, mainly due to the relative limits of the galactic environment. Most of these particles are accelerated by supernova explosions or the remnants of massive stars that create shock waves that can propel particles to high speeds while remaining powerful. These galactic rays usually have less energy compared to their extragalactic counterparts, which can come from extreme and extremely energetic phenomena, such as quasars or gamma-ray bursts. An intriguing aspect of these cosmic rays is how they interact with the Earth's atmosphere. Galactic cosmic rays tend to be more abundant and common near our planet, while extragalactic rays, although rarer, can have immense energies that sometimes cause spectacular showers of particles when they collide with particles in the atmosphere. These interactions can create secondary particles that allow scientists to trace the origin of these energetic phenomena and understand the mechanisms that drive them. The study of cosmic rays is not limited to understanding the particles themselves, but opens a window to the processes that shape our universe by analyzing the differences between galactic and extragalactic cosmic rays. Researchers can gain information about the environments in which they occurred and the fundamental physics that governs those celestial phenomena. It is a fascinating realm that connects us deeply with the universe beyond our planet. The EDGE's signal refers to a revolutionary observation made by an international team of scientists using the experiment to detect the global signature of the era of reionization. This experiment aimed to understand the radio waves emitted by neutral hydrogen in the early universe, specifically during a period known as the Cosmic Dawn, which occurred approximately 400 million years after the Big Bang. What the team detected was a surprising drop in the intensity of radio signals at a specific frequency, a signal that should not have been present according to existing cosmological models. This observation poses an enigma for scientists. According to conventional theories, we would expect to measure a uniform temperature in the universe during that time, but the signal from the edges implies that the cosmic microwave background radiation was much colder than expected. This finding suggests that something extraordinary must have happened with the hydrogen gas in the early universe, which caused cooling and created the conditions that produced this anomalous signal. These findings challenge ingrained beliefs about how matter and radiation interacted in those early moments of cosmic history. One possible explanation is that there could have been exotic physics or interactions at play, such as the presence of dark matter that interacts more intensely with the baryonic matter than was thought. The idea here is that this could have created a colder temperature for the hydrogen gas, effectively altering the signals coming from the vast universe. This raises fundamental questions about our understanding of dark matter and its role in cosmic evolution. Ultimately, the signal from the edges not only intrigues scientists, but also opens new avenues for research into the infancy of the universe. This emphasizes that our understanding of the cosmos continues to evolve as we collect new data. Each signal we receive from the immense expanse of space brings us closer to unraveling the mysteries of the universe, leading us to rethink theories based on decades of observations. The mystery of lithium-7 in the universe is a fascinating story that is nourished both by the history of our cosmos and by the limits of our knowledge. Lithium-7 is one of the lightest elements that formed shortly after the Big Bang, during a period called Big Bang nucleosynthesis. This process was crucial for the creation of the lightest elements: hydrogen, helium, and very small amounts of lithium and beryllium. Scientists had predicted certain proportions of these elements based on theoretical models, but observations reveal an unexpected shortage of lithium-7. The apparent lack of lithium-7 is disconcerting because measurements of the abundance of the elements have important implications for our understanding of the early universe. When astronomers observe older stars, they find lower concentrations of lithium-7 than theoretical models suggest should exist. This discrepancy has led scientists to explore various explanations, each of which reveals a deeper layer of cosmological knowledge. One prominent theory proposes that certain astrophysical processes could systematically destroy lithium-7 in stars. As stars evolve, they undergo thermonuclear fusion reactions that can break down lithium. This means that although lithium was formed during the Big Bang, the processes inside the stars corroded over time, leading to the observed deficiencies. Another possibility is that the initial conditions of the universe were different from what we currently understand. Some researchers argue that there may have been less lithium produced shortly after the Big Bang than was previously thought, or perhaps the chemical pathways have not been entirely correct in our nuclear synthesis models. Each new observation brings us a step closer to unraveling this enigma. Testimony to the evolving nature of scientific research, the story of lithium-7 is not only about missing elements, but emphasizes an ongoing dialogue in science in which questions drive discovery, revealing the complex narrative of the early moments of our universe. The distribution of satellite galaxies around our Milky Way and the Andromeda galaxies is an enigma in cosmology that has intrigued astronomers for years. We generally think of galaxies as large expanding structures with a predictable halo of smaller satellite galaxies surrounding them. However, the arrangement of these satellites reveals some surprising patterns that suggest that there are deeper cosmic principles at play. A key aspect contributing to this unexpected distribution is known as the ring effect. This effect postulates that satellite galaxies are not limited to randomly floating around their host galaxies, but that the greater gravitational influence of the Milky Way and Andromeda can drag small galaxies into distinct trajectories around them. This causes the satellites to align along certain planes rather than being evenly distributed in three-dimensional space, giving them a kind of ring-shaped structure that is not what one would expect when observing galaxy models. Furthermore, the role of dark matter, which constitutes a significant part of the mass of the universe, does not emit light and is invisible to our instruments, cannot be underestimated. However, its gravitational effects are profound. The halos of dark matter surrounding these galaxies influence how visible matter behaves, including satellite galaxies. This gravitational pull can shape the orbits and distribution of the satellites, resulting in their clustering around certain regions rather than a random dispersion. These phenomena suggest a rich environmental interaction within the cosmos and point to the intricate dance of galaxies influenced by gravity, dark matter, and fundamental cosmic forces. The resulting arrangement of the satellites is not just an afterthought of a galaxy, but a reflection of the complex dynamics that govern its formation and evolution in the universe. As we learn more about these interactions, our understanding of the cosmos continues to deepen, revealing the beautiful complexity hidden within the stars. Researchers have long been fascinated by the discovery of extremely massive galaxy clusters that exist in the early universe, a finding that challenges our traditional understanding of cosmic evolution. These clusters, composed of thousands of galaxies, large amounts of gas, and dark matter, are believed to have formed when the universe was still quite young. The existence of such massive structures so soon after the Big Bang raises important questions about how they could accumulate enough mass in such a short time. One of the key explanations has to do with the role of dark matter, which constitutes a significant part of the total mass of the universe. Dark matter does not emit light and is invisible, but it has a gravitational effect on visible matter. Researchers propose that dark matter began to clump very early in the history of the universe, forming the gravitational scaffolding around which ordinary matter could clump. This process may have allowed enormous clusters to form faster than previously thought. Another significant aspect of this phenomenon is the influence of cosmic inflation. This theory suggests that, after the Big Bang, the universe underwent a rapid expansion that smoothed out energy fluctuations in space. These fluctuations could have created the seeds of large-scale structures, allowing certain regions to have more matter that later clumped into massive clusters. Thus, while the universe was only a few billion years old, some areas became exceptionally dense, leading to the formation of these enormous clusters. Finally, supercomputer simulations of cosmic evolution have also shed light on this mystery. These simulations replicate billions of years of cosmic interactions and have shown that, under the right conditions, massive clusters can form much earlier than our traditional cosmological models predict. By combining telescope observations with theoretical models, researchers are slowly getting closer to understanding how the architecture of the universe took shape so quickly after its inception. This exploration of the cosmos not only deepens our understanding of the formation of clusters of galaxies, but also invites us to reflect on the greatest mysteries of our universe. The cosmic microwave background, or CMB, is a remnant from the early universe, providing a snapshot of the cosmos just after the Big Bang. One fascinating characteristic of the CMB is its hemispherical asymmetry, where we observe subtle differences in temperature and structure across the sky. This asymmetry raises intriguing questions about the processes that shaped the early universe. The importance of this hemispherical asymmetry lies in what it can reveal about the universe's formation and evolution. Observations indicate that one hemisphere of the sky appears slightly warmer and denser than the other. This could suggest variations in the distribution of matter during the early stages of the universe, or point to the influence of large-scale structures, such as clusters of galaxies, which could have affected the characteristics of the CMB. Furthermore, this asymmetry challenges our understanding of cosmic inflation theory, which states that the universe underwent rapid expansion in its earliest moments. Inflationary models often predict a uniform distribution throughout the CMB, so the presence of this asymmetry invites scientists to explore new theories or modifications of existing ones. It could even hint at interactions with other universes or extra dimensions, though these ideas are speculative. As researchers continue to study this phenomenon, they employ advanced observation techniques and theoretical models to analyze the numerous layers of information of the CNB. The search to understand hemispherical asymmetry is not limited to temperature fluctuations, but is a window into the very structure and history of our universe, providing clues that could one day redefine our understanding of the cosmos.